Please subscribe to support the channel. There is a secret lurking in the night sky, a faint, nearly invisible point of light that carries within it the promise of becoming the most dazzling spectacle humanity has ever seen. Astronomers have studied thousands of stars, mapped galaxies beyond counting, and traced the faintest whispers of light from the edge of the observable universe. Yet hidden among the countless stars of the Milky Way, there lies one that is unlike any other. This is not a star that merely flickers or brightens on occasion. This is a celestial system that scientists believe will one day transform itself into a beacon so bright, so radiant, that it will rival the glow of the moon itself. They predict that when this moment comes, all other stars will pale in comparison, and for a time, the night sky will be utterly transformed by a single star's brilliance. This is no ordinary prediction. It is a rare forecast of an event written in the physics of stellar evolution, a countdown to a cosmic outburst already set in motion millions of years ago. The mystery surrounding this star is not only about what it will become, but also about the fact that humans alive today already know of its fate. We stand at a unique moment in history, holding knowledge of a spectacle that will unfold with breathtaking drama within the lifetime of our children or grandchildren. When this star erupts into brilliance, it will be visible from every corner of Earth, without the aid of a telescope, without the need for dark skies. Whether you are in a bustling city or a remote desert, its light will cut through the atmosphere and command attention. For weeks, perhaps even months, this star will dominate our night sky, an unmissable reminder of the raw, explosive forces that shape the universe. But what makes this story even more captivating is the element of certainty. Throughout history, humanity has recorded sudden, unexpected eruptions of stars, novae, supernovae, and other cataclysmic outbursts that seem to arrive without warning. Ancient civilizations would look up and see a new star appear in the heavens, brighter than anything else, and wonder if it was an omen. We today, however, find ourselves in an extraordinary position. We already know the name of the star, the nature of its system, and even the approximate year when its great transformation will occur. That in itself is something unprecedented, almost like knowing the exact year when a mountain will erupt or a great comet will blaze across the sky. Astronomers have traced the forces at work within this star system and followed its long, slow journey toward inevitability. Their calculations suggest that the climax of this drama is set to occur around the year 2083, a date now etched into the annals of science as a moment when humanity will witness the sky itself change before our eyes. Some say it may come earlier, others caution it may arrive later, but the outcome remains certain. This star will outshine every other object in the heavens apart from the sun and the moon. As we prepare to unravel this story step by step, we will uncover the identity of this mysterious star, learn where it hides in the sky, explore the science that drives its coming explosion, and reflect on what it means for humanity to be able to anticipate such a cosmic event. This is a tale of science, wonder, and inevitability. A story that begins quietly with a faint, unremarkable star and ends with an eruption of light so intense that it will echo through human history. The veil of mystery around this extraordinary stellar drama lifts when we finally speak its name. The star that astronomers have identified as the protagonist of this cosmic spectacle is called V Sagittae. To the untrained eye, this name might sound obscure, perhaps even forgettable, but hidden in those two words lies a tale of enormous significance. V Sagittae is not one of the celebrated stars that poets, philosophers, or astronomers of antiquity wrote about. It does not shine like Sirius, blaze like Betelgeuse, or inspire myths like Orion's belt. In fact, for nearly all of human history, it was completely invisible to the naked eye, tucked away so faintly that no one suspected it of harboring one of the most dramatic fates in the galaxy. And yet, in a twist of cosmic irony, this faint and largely forgotten star is destined to become the brightest of them all. The naming of V Sagittae follows the conventions astronomers use to catalogue variable stars, stars whose brightness fluctuates over time. The V designation does not stand for a grand word like victory or vision, but simply indicates that this star is part of a long-running sequence of variables catalogued in its constellation. V Sagittae happens to be the very first variable star discovered in the small constellation Sagitta, which means the arrow. That's where the V comes from. It's essentially shorthand for variable star in Sagitta. While the name may not sound poetic, the reality behind it is breathtaking. It is almost as though this unassuming label conceals a secret waiting to be revealed, a cosmic arrow poised to be released across the sky in the 22nd century. When astronomers first attached this humble designation to V Sagittae, they could not have guessed the importance it would later hold. Back then, it was just another dim and changeable point of light among countless others. Yet over the decades, careful observations began to uncover a story hidden in the star's faint flickers. Its light varied in ways that hinted at unusual dynamics beneath the surface, suggesting that there was more to V Sagittae than met the eye. Each observation brought scientists a little closer to realizing that this unremarkable object was in fact one of the most extraordinary systems in the galaxy. To appreciate just how special V Sagittae is, it's worth pausing to consider how easily it could have remained unnoticed. Our galaxy contains hundreds of billions of stars, many of them variable, many of them interacting in pairs or groups. Astronomers catalog them diligently, but most are relegated to the quiet pages of star atlases and databases, visited only by researchers with very specific interests. V Sagittae might have stayed in obscurity forever had it not been for the dogged persistence of astronomers who studied its peculiar behavior. Through their observations, the star slowly revealed its secret. It is part of a binary system that is locked on a collision course, a celestial countdown already underway. That is why today, when we say the name V Sagittae, we are not simply naming a faint dot of light. We are invoking a prediction, a promise of the future. This little-known system, hidden in one of the sky's smallest constellations, will someday dominate the heavens. For a short while, everyone on Earth, astronomers, stargazers, and ordinary people who rarely look up, will know its name. V Sagittae will pass from the domain of obscure astronomical catalogues into the shared memory of humanity as the star that transformed night into day. It is fascinating to imagine that, even now, while it remains invisible without telescopes, the star is already famous among scientists. Professional astronomers talk about V Sagittae with the same excitement that one might reserve for a comet whose orbit promises a spectacular return. Amateurs who know where to look sometimes target it with their telescopes, aware that they are observing a future legend. The very act of finding it today feels like glimpsing destiny in its quiet, unassuming stage. And yet, despite this knowledge, for most people, V Sagittae remains an unknown name. If you asked a random person about it, they would almost certainly have never heard of it. That, too, adds to the poetic drama of this story, the idea that the brightest star of the future is still invisible to the naked eye and largely absent from popular imagination. In a way, it mirrors the countless overlooked forces in the universe, those quiet, invisible processes that, given enough time, unleash unimaginable transformations. When the year 2083 arrives and V Sagittae fulfills its fate, the name will no longer be obscure. It will appear in headlines, be discussed in classrooms, and inspire artists, writers, and dreamers. Generations who grow up under its glow will remember it as the defining celestial event of their lives. And for those who know its story now, there is a sense of anticipation, of knowing that the star whose name we whisper today will one day shout across the heavens with light powerful enough to rival the moon. To truly understand V Sagittae and its story, we must first travel to its celestial neighborhood, an unassuming patch of sky that most people have never noticed. V Sagittae resides in the constellation of Sagitta, which means the arrow in Latin. Unlike the sprawling majesty of Orion or the regal brilliance of Ursa Major, Sagitta is a remarkably tiny constellation, tucked away almost shyly among its brighter neighbors. Its shape is simple, a small arrow pointing across the heavens, but its diminutive size makes it easy to overlook. In fact, Sagitta is the third smallest constellation in the entire sky, out of the 88 officially recognized constellations. And yet, despite its modest proportions, it hides within it a star destined for cosmic fame. If you were to step outside on a clear night and scan the skies, finding Sagitta would not be easy. It lies nestled in the rich region of the Milky Way, surrounded by far brighter constellations. Just to its west lies Aquila, the eagle, home to the brilliant star Altair, one of the 3 points in the famous Summer Triangle. To its east is Vulpecula, the little fox, and further along stretches Cygnus, the swan, soaring across the sky with its magnificent cross-shaped pattern. Amid these commanding constellations, Sagitta is almost swallowed up, like a quiet whisper among powerful voices. Its stars are faint, none brighter than 4th magnitude, which means they don't stand out to casual stargazers. You need dark skies and a patient eye to trace its delicate arrow shape. The constellation itself is not dramatic in appearance. Its 4 main stars form a narrow line, like a shaft, with two others making up the tip of the arrowhead. Unlike Orion, which dominates winter evenings, or Scorpius, whose curving tail is instantly recognizable, Sagitta demands careful attention. Many stargazers might sweep right over it without ever realizing they passed a constellation at all. And yet, tucked within this miniature figure, near its shaft, lies V Sagittae, a star so faint today that even if you knew exactly where to look, you'd need at least a pair of binoculars, if not a telescope, to see it. This contrast is part of what makes V Sagittae's story so captivating. Right now, it hides in plain sight, lost in the river of the Milky Way, overshadowed by the brilliance of its neighbors. It is almost as if nature itself wanted to keep the star's true destiny a secret until humanity had the tools to uncover it. Before the invention of telescopes, no ancient culture could have known V Sagittae existed. While civilizations built myths around the likes of Orion, Cassiopeia, and Scorpio, V Sagittae slumbered unnoticed, awaiting the day it would earn its place in human lore. For amateur astronomers today, locating Sagitta is a small but satisfying challenge. The easiest way is to start with the summer triangle, Altair, Deneb, and Vega. From Altair in Aquila, draw your eye eastward along the Milky Way, and you'll find a faint, arrow-shaped pattern pointing roughly toward Vulpecula. That's Sagitta. Once you've pinned it down, you can trace its tiny shaft and head, and, with a telescope, pick out V Sagittae lurking within. Doing so is a humbling experience. Because when you see that faint speck, you're staring at the future brightest star in the sky. The location of Sagitta also means that when the great outburst of V Sagittae finally comes, it will be in a very favorable position for observers around the world. Because it lies along the Milky Way near the celestial equator, it will be visible from both the northern and southern hemispheres. This ensures that when the star explodes into brilliance, no one on Earth will miss it, regardless of geography. It will not be one of those cosmic spectacles limited to a lucky few. Instead, it will be a truly global event, a star placed by fate in just the right spot for the entire planet to witness. For now, though, Sagitta remains a curiosity for those who love the challenge of finding faint constellations. It is a place of quiet beauty, often overlooked in favor of its neighbors. And hidden within it is a faint star that currently contributes nothing remarkable to the night sky. But knowing its future changes everything. When you look towards Sagitta, you are gazing not at a forgotten corner of the heavens but at the stage upon which one of the greatest astronomical events of human history will play out. The story of V Sagittae's discovery is, in many ways, the story of how modern astronomy has learned to see the hidden layers of the universe. Unlike the brilliant stars that guided sailors across oceans or inspired mythologies, V Sagittae never stood out to the naked eye. Its light was too faint, its presence too subtle, for ancient skywatchers to notice. To them, the patch of sky where Sagitta lies was nothing more than a faint smudge in the river of the Milky Way, unworthy of myth or legend. It wasn't until the age of telescopes and systematic sky surveys that this humble star was brought into human awareness. The first catalogued observations of V Sagittae go back to the early 20th century, when astronomers, equipped with increasingly powerful photographic plates, began to notice that certain stars did not behave as expected. In 1902, astronomers recorded that the star was variable. It changed brightness over time. This was unusual enough to earn it a designation in the catalogues of variable stars, where it was officially christened V Sagittae, the first variable star discovered in the tiny constellation of Sagitta. At the time, though, this discovery was treated as little more than a footnote. The universe is littered with variable stars, many of them far brighter and more dramatic than this faint, 10th magnitude flicker. For decades after its initial discovery, V Sagittae remained a scientific curiosity rather than a star of great importance. Astronomers recorded its fluctuations, noted its faintness, and placed it among the many hundreds of other variables known in the Milky Way. In those years, it was considered simply another point of light that changed brightness unpredictably, offering some opportunities for study but nothing revolutionary. Even the name itself, as we've mentioned before, is humble, V for variable, followed by the constellation in which it resides. No dramatic mythological title, no grand flourish, just a catalogue number in the long list of stars. But as the 20th century progressed, new tools and techniques began to peel back the layers of what was really happening in this system. Photographic plates gave way to sensitive electronic detectors, and astronomers were able to chart the star's light variations in far greater detail. What they found hinted at complexity beneath the surface. V Sagittae was not merely variable in the simple sense, like Cepheids that pulse steadily or eclipsing binaries that dim as one star passes in front of another. Its fluctuations were chaotic, unpredictable, and far more dramatic than those of most stars in its class. Something unusual was happening here. At first, astronomers categorized it alongside other stars known as cataclysmic variables. Stars that undergo sudden, dramatic outbursts in brightness due to the interactions within binary systems. Cataclysmic variables were already a fascinating field of study, involving white dwarfs feeding on companion stars and producing nova-like eruptions. V Sagittae fit into this group, but it was not until decades later that scientists began to realize just how unique it was, even among these explosive stellar families. Early observations treated its outbursts as curiosities, but as astronomers gathered more and more data, a clearer picture emerged. The star's light curve, the pattern of its brightening and fading, hinted at an unusually tight binary system. Spectroscopic studies revealed that its spectrum contained signs of material swirling at incredible speeds, and emissions that suggested a violent transfer of mass from one star to another. These were the early breadcrumbs that would eventually lead scientists to the astonishing conclusion. V Sagittae was on a trajectory unlike any other known system, a runaway train headed for cosmic detonation. But let's linger for a moment on what it must have been like in those early years, before the significance was understood. Imagine the astronomers of the early 1900s, working with bulky telescopes and photographic plates coated with chemicals, spending long, cold nights under the stars. Their plates captured hundreds of faint stars at a time, and only later, when carefully examined under magnification, would subtle changes emerge. A star like V Sagittae, faint and seemingly unimportant, would flicker just enough to draw attention. Variable, they would note, perhaps with a shrug. For them, it was one of many, another addition to the growing census of the sky. They could never have guessed that the faint speck they catalogued in such a routine way would become, in the far future, the brightest star in Earth's sky. It's a poignant reminder of how science often works. Great discoveries are not always heralded with fanfare at the moment of their first detection. Sometimes they hide quietly in data tables, waiting for future generations with better tools and sharper theories to uncover their true importance. V Sagittae is one of those cases, a faint star discovered in 1902, filed away as variable, then slowly, over the course of decades, revealed as one of the most extraordinary systems in the galaxy. Today, when we look back on its first discovery, it's almost surreal to think how unremarkable it seemed. To the astronomers of the early 20th century, it was a curiosity at best. To us, it is a ticking clock, a countdown to one of the brightest and most predictable stellar explosions humanity has ever had the chance to witness. The long journey from obscurity to fame began with that first catalogue entry, that first acknowledgement that something about this faint star was worth noting. Without that initial step, V Sagittae's destiny might still be hidden in plain sight. When astronomers first turned their instruments toward V Sagittae in greater detail, they assumed they were looking at a single star. After all, that is how most stars present themselves: one source of light, one object twinkling faintly in the night sky. But as decades of careful study revealed, V Sagittae was hiding a profound secret. It is not one star at all, but two stars locked in a perilous embrace. This revelation changed everything. The flickering and chaotic brightness variations that had puzzled early observers suddenly made sense when seen through the lens of a binary system. What appeared faint and unremarkable to the naked eye was, in reality, a stage for one of the most violent stellar relationships in our galaxy. The concept of binary stars is not rare in itself. In fact, modern astronomy has shown that most stars in the universe are not solitary like our Sun, but instead are members of binary or even multiple star systems. Two stars orbiting each other around a common center of mass is almost the norm rather than the exception. Some binaries are wide and gentle, their stellar companions separated by vast distances, revolving around each other over centuries. Others are close, circling in mere days or hours. And it is within these tight systems that the most dramatic interactions occur, where gravity tugs, matter transfers, and sometimes explosive consequences unfold. V Sagittae belongs to the latter category, a close binary system so tight and dynamic that the fate of both stars is sealed. What astronomers discovered through spectroscopy, the study of light spread out into its component wavelengths, was that V Sagittae's light contained signatures of two distinct objects. Not one, but two stars were there, bound together in a gravitational waltz. Their mutual pull was so strong and so close that their orbits were measured not in centuries, or even years, but in mere hours. This immediately placed V Sagittae among the most intriguing binaries known. To grasp the significance of this discovery, we must understand how such close binaries operate. Picture two stars orbiting so near each other that their gravitational fields overlap. In such cases, the more massive star exerts a relentless pull on its companion, often siphoning off material from it in a process that creates luminous displays of gas and light. This interaction can power eruptions, novae, or even lead to complete stellar mergers. The closer the stars, the more violent and inevitable their interactions become. V Sagittae is an almost textbook example of this phenomenon, but with a twist that makes it uniquely important. Within V Sagittae, the two stars are fundamentally different types of objects. One is a normal star, still burning hydrogen in its core, somewhat like our Sun though smaller in mass. The other, however, is a white dwarf, the collapsed, dense remnant of a star that has already reached the end of its normal stellar life cycle. This pairing sets the stage for drama. The normal star is essentially a fuel source, while the white dwarf is a cosmic predator, feeding off its companion with a gravitational appetite that only grows stronger as the system evolves. At first, astronomers were puzzled by the star's irregular flickering. Some nights it was slightly brighter, others dimmer, and sometimes it underwent outbursts of unusual luminosity. Only when they realized they were dealing with a binary system did the pieces fall into place. Those variations were not the random whims of a single star but the visible evidence of a constant struggle between two celestial bodies. Light from the system was changing because material was being stripped from one star, funneled into the other, and periodically erupting in bursts of energy. The discovery that V Sagittae was binary also transformed its classification. No longer was it just another variable star. Instead, it became part of the family of interacting binaries, specifically a type of system where a white dwarf pulls material from a companion. This placed it in the same general class as cataclysmic variables, a group of systems known for sudden, explosive brightening. Yet, even here, V Sagittae proved unusual. Most cataclysmic variables have a white dwarf significantly more massive than their donor star, allowing them to maintain a sort of grim equilibrium for long periods. But in V Sagittae, the balance is reversed. The donor star, the so-called normal star, is actually more massive than the white dwarf. That imbalance is key to its unique fate, setting it apart from nearly every other known binary system. When scientists pieced all this together, they realized they were watching not just a binary star system but a binary in crisis. The normal star is being consumed, its gas funneled onto the white dwarf, but because it is the larger of the two, the process cannot stabilize. The transfer accelerates, creating a runaway situation. This is why V Sagittae does not simply behave like other binaries but instead races toward a catastrophic climax. It's almost poetic that V Sagittae, once dismissed as faint and unremarkable, turned out to be a binary, a system of two entwined stars rather than one. It mirrors the story of its discovery. What seemed ordinary at first glance revealed itself to be extraordinary under closer inspection. Binary systems are sometimes compared to cosmic marriages, with all the drama and intimacy that comes from two entities bound together. In the case of V Sagittae, it is a marriage headed for fiery divorce, an inevitable collision of fates that will culminate in a spectacular outburst visible across Earth. Understanding that V Sagittae is binary is the first step toward unraveling why it is destined to shine brighter than any star we've ever seen. Without the binary nature, without the interplay of these two very different stars, the system would be just another faint point of light. But together, locked in orbit, locked in conflict, they set the stage for one of the most dramatic shows the cosmos has scheduled for us. At the heart of V Sagittae's drama are its two main players, a mismatched pair of stars bound by gravity yet fated to destroy each other. To understand why this system is unlike almost any other in the sky, we need to look closely at each star in the pair: the donor, a so-called normal star, and the devourer, a dense white dwarf. On their own, each would be fascinating. Together, they create one of the most violent and inevitable stellar interactions astronomers have ever seen. Let us start with the donor star. It is often described as a main sequence star, meaning it is in the same broad category as our Sun, a star that burns hydrogen in its core through nuclear fusion. But unlike our Sun, this star is not a steady beacon of stability. For one thing, it is more massive than its white dwarf companion, and in close binaries, mass matters enormously. Mass dictates who pulls on whom, who loses and who gains, and what the long-term fate of the system will be. In most interacting binaries, the white dwarf is heavier, and it steals matter from a lighter companion in a relatively balanced, though destructive, way. In V Sagittae, the donor is actually more massive than the white dwarf, an unusual reversal of roles that sets this system apart from the norm. The donor star is also swollen compared to its white dwarf partner. Its outer layers are not tightly bound, which makes them vulnerable to gravitational theft. Imagine a star whose gases are like a loose cloak, drifting outward. Place a powerful gravitational object nearby, and that cloak can be pulled off, streaming into space. That is exactly what is happening here. The donor star is being stripped, piece by piece, of its outer layers. Its mass is slowly but surely flowing toward its hungry companion. Now let's turn to the second player, the white dwarf. This is no ordinary star. A white dwarf is what remains when a medium-sized star, like our Sun, reaches the end of its life. After billions of years of burning hydrogen, such a star exhausts its fuel, sheds its outer layers into space, and leaves behind a small, dense core. That core, no longer powered by fusion, becomes incredibly compact. A white dwarf typically packs a mass comparable to the Sun into a volume no larger than Earth. To grasp its density, picture a teaspoon of white dwarf material weighing several tons. It is matter under crushing pressure, the end state of a star that has collapsed into an object of staggering compactness. The white dwarf in V Sagittae is the vampire of the system, feeding relentlessly on its companion. Its gravity is immense, and because it orbits so close to the donor star, it draws gas away with irresistible force. This stolen gas does not simply fall straight onto the white dwarf. Instead, it spirals in, forming what astronomers call an accretion disk, a swirling ring of matter heated to incredible temperatures as friction and gravity tear it apart. This disk glows brightly, producing much of the chaotic light variations astronomers observe from Earth. So, on one side, we have the donor star, a larger, more massive object that is doomed because of its proximity and vulnerability. On the other side, we have the white dwarf, a small, dense, but ravenous remnant of stellar death. Their relationship is both intimate and destructive. They orbit each other at such close range that the entire cycle of their dance takes mere hours. Think about that. Two stars, each with masses measured in solar units, circling each other faster than most of us could drive to work. Their closeness is the key to their fate. At this distance, no equilibrium can last. The imbalance of mass is what seals the system's destiny. Because the donor is more massive, the transfer of material onto the lighter white dwarf causes a runaway effect. Instead of stabilizing, the flow of gas accelerates. The more the donor loses, the faster it loses what remains. The more the white dwarf gains, the more gravitational pull it exerts. It is a feedback loop with no brakes, a process that can only end in catastrophe. Individually, these two stars tell powerful stories about stellar life cycles. The donor star shows us the everyday process of hydrogen fusion, the steady life of a star not too different from countless others scattered through the galaxy. The white dwarf, on the other hand, tells us about stellar death, the collapsed remains of a star that once burned brightly but has since shed its outer beauty and shrunk into a dense ember. Together, however, they tell a story about stellar cannibalism, how one star's death becomes another's doom, and how gravity can bind two stars into a relationship so extreme that it guarantees their destruction. In many ways, the pairing in V Sagittae is like a cosmic allegory. The donor star, larger and seemingly stronger, is undone by the smaller but denser white dwarf. Size is no guarantee of survival. In this case, density and gravity are what matter. The white dwarf, though tiny in comparison, has the advantage of compactness. Its gravity acts like a siphon, pulling life away from its companion. It is a predator hiding in plain sight, drawing its victim closer and closer until the end is inevitable. When astronomers describe V Sagittae today, they no longer speak of it as a star but as a binary system of extremes. The donor and the white dwarf are not separate stories but parts of a single narrative, a fatal dance that will culminate in one of the most brilliant stellar events ever recorded. Knowing their individual characteristics helps us understand the mechanism, but it is their interaction, the clash of normal and collapsed, of massive and dense, that makes this system unique. When we talk about stars orbiting each other, the distances are usually staggering. In many binary systems, stars are separated by tens or even hundreds of millions of kilometers, leisurely circling each other over decades or centuries. But V Sagittae does not belong to that calm category. The two stars in this system are locked in an orbit so tight and frantic that it defies everyday imagination. Their relationship is not a slow waltz but a desperate, clinging spiral, a dance so close that it is measured in hours rather than years. Let's put this into perspective. The Earth orbits the Sun once every 365 days at an average distance of about 150 million kilometers. Even the innermost planet, Mercury, takes 88 days to make its trip. Yet in V Sagittae, these two stars, both with masses comparable to, or greater than, our Sun, complete a full orbit around one another in just about 12 hours. Half a day. By the time you wake up, go to work, and return home, these two massive stars have already completed their dizzying embrace. The distance separating them is mind-bendingly small by stellar standards. Instead of millions of kilometers, they are separated by only a few solar radii, roughly comparable to the diameter of our Sun itself. Imagine compressing two stars, each blazing with nuclear fire or collapsed into crushing density, into a system where their surfaces are practically brushing up against each other. This is not just close, it is intimate, dangerous, and unstable. At this range, their gravitational interaction is overwhelming. Each star's gravity distorts the other, pulling it into an elongated, teardrop-like shape rather than a perfect sphere. Astronomers call this a Roche lobe, the gravitational boundary around each star. In V Sagittae, the donor star has overflowed its Roche lobe, meaning its outer gases no longer remain bound to itself. Instead, they are spilling across the gravitational divide, flowing directly toward the white dwarf. This is not a trickle, it is a river of stellar material, constantly streaming from one star to the other. The orbital speed involved is equally astonishing. To maintain a 12-hour orbit at such a small separation, each star must be moving at hundreds of kilometers per second relative to the system's center of mass. These are velocities that dwarf anything we know in human experience. Even the fastest spacecraft humanity has ever built crawl compared to the ferocious speed at which these stars chase each other around their mutual orbit. It is this velocity, this closeness, that amplifies the violence of their interaction. Because they are so close, the entire system is unstable. The white dwarf is not merely passively drawing in gas, the donor star is being actively shredded by tidal forces. Each orbit destabilizes it further, stripping more gas, accelerating the process of mass transfer. The tighter the orbit, the more intense the transfer. And the more intense the transfer, the more energy is released in bursts of radiation, which we observe as flickering light here on Earth. This explains why V Sagittae's brightness appears erratic and unpredictable. It is the visible evidence of a catastrophic relationship happening in real time. This extreme proximity is what makes V Sagittae's future so certain. In wider binaries, stars can coexist for millions or even billions of years before one finally steals enough matter from the other to trigger a nova or supernova. But in this system, the closeness accelerates everything. There is no long-term equilibrium possible. The donor is too close, the pull of the white dwarf is too strong, and the orbit is too fast. All of these factors together create a runaway situation, a countdown clock that cannot be stopped. Astronomers sometimes describe this system as spiraling toward doom. That phrase is not metaphorical. Because of the orbital dynamics and the constant exchange of mass, the two stars are gradually tightening their embrace. Over time, the separation shrinks further. Each orbit brings them microscopically closer together, each revolution increasing the pressure. It is as though the stars are locked in a death spiral, with no escape. For us, peering across thousands of light-years, this proximity is invisible to the naked eye. All we see, or would see, with the right telescope, is a faint, flickering point of light. But hidden within that tiny point is a furious dance happening on scales far beyond human comprehension. Two stars, separated by a distance smaller than the diameter of the Sun, orbiting each other with breakneck speed, tearing each other apart. The closeness of this orbit also helps. Explain why scientists can predict the system's fate with such confidence. The physics of binary systems is well understood. Once you know the masses, the separation, and the rate of mass transfer, you can model the system's future with remarkable precision. In V Sagittae's case, those calculations all point to the same conclusion. This unstable, close orbit is a prelude to a runaway event, an explosion of brightness that will turn a faint star into the most dazzling beacon in the sky. And perhaps most striking of all, this is happening not in some distant galaxy we will never touch, but right here in our own Milky Way. In astronomical terms, V Sagittae is practically a neighbor, close enough that when it erupts, its light will rival the moon. That proximity, on both the orbital and galactic scale, adds to the sense of awe. We are watching a pair of stars so close together that they are tearing each other apart, and we know that the climax of their story will unfold within the human timescale of history. A white dwarf is one of the most remarkable objects in the universe, and to understand the drama of V Sagittae, we need to pause and explore exactly what this kind of star is. For many people, when they think of stars, they picture blazing spheres like our Sun, massive furnaces where hydrogen is fused into helium. That stage of life is only part of a star's story. Stars, like living things, are born, they age, and they die. And in many cases, what remains after a star has burned through its fuel is not a fiery sun-like orb, but a white dwarf, the dense, collapsed core of a once-living star. The journey toward becoming a white dwarf begins with stars of low to intermediate mass, roughly up to 8 times the mass of our Sun. These are stars that shine steadily for billions of years, consuming their hydrogen fuel. At the start, hydrogen fuses into helium in their cores, releasing energy that pushes outward against the immense pull of gravity. This balance between outward pressure and inward pull keeps the star stable for most of its life. But hydrogen is finite, and once it runs out in the core, the balance begins to falter. When the core hydrogen is exhausted, the star begins fusing hydrogen in a shell surrounding the core, while the core itself contracts and heats up. This causes the star to swell into a red giant, an enormous, bloated version of its former self. Our Sun, in about 5 billion years, will go through this phase, swelling large enough to engulf Mercury and possibly Venus. During this red giant stage, new layers of fusion occur, creating helium into carbon and oxygen. The process is turbulent, unstable, and accompanied by powerful stellar winds that blow away the star's outer layers into space. Eventually, the star can no longer sustain nuclear fusion. The outer layers drift away, forming a beautiful planetary nebula, a glowing shell of gas expanding into space. What remains at the center is the star's naked core. Without fusion to support it, gravity takes over, compressing the core into an object so dense that its matter is unlike anything we experience on Earth. This is the white dwarf. A white dwarf is typically about the size of Earth, yet it contains a mass comparable to the Sun. Imagine taking the weight of our entire star and squeezing it into a ball no larger than our planet. The density is staggering. A teaspoon of white dwarf material would weigh several tons on Earth. This crushing compactness is supported not by the pressure of fusion but by what physicists call electron degeneracy pressure, a quantum mechanical effect that prevents the particles inside from collapsing any further. In this way, the white dwarf achieves a strange kind of stability. It no longer burns fuel, but it resists total collapse through the peculiar laws of quantum physics. White dwarfs shine faintly at first, not because they generate new energy, but because they retain the heat of their former life. Over billions of years, they slowly cool, radiating away their stored heat until they become cold, dark remnants called black dwarfs, though the universe is not old enough for any to exist yet. Even so, the existence of white dwarfs tells us something profound about the life cycle of stars. They are the embers of once living suns, the fossilized remains of nuclear furnaces that lit up the galaxy in their youth. The white dwarf in V Sagittae is exactly such a remnant. It was once a normal star, not too different from our Sun, that lived out its long life of fusion, expanded into a red giant, and then shed its outer layers. What remains now is its core, small and dense, a gravitational powerhouse waiting in orbit beside its companion. But while most white dwarfs quietly cool in space, fading into obscurity, this one has found itself in an extraordinary situation. It is so close to another star that it has become a predator. Its intense gravity pulls gas away from its companion, stripping hydrogen and helium from the donor and feeding upon it. In effect, the white dwarf has been given a second chance to burn brightly, not through its own fusion, but by consuming the life of another star. This makes white dwarfs both eerie and fascinating. They are dead stars, yet they can flare back into brilliance when given fresh fuel from a companion. In V Sagittae, this process is not gentle. The accreted gas piles up on the white dwarf surface, heating under immense pressure until it triggers violent reactions. Over time, the white dwarf's hunger grows insatiable, pulling more and more material. Because the donor star in this case is unusually massive, the imbalance accelerates the process beyond anything seen in typical binaries. That is why V Sagittae is not destined to remain stable but instead will blaze out in a runaway explosion. Thinking about what a white dwarf is also invites us to reflect on our own sun's distant future. Billions of years from now, our sun will end its life in much the same way. It will swell into a red giant, shed its outer layers, and leave behind a white dwarf. But unlike V Sagittae, our sun is alone. It has no companion to feed upon, no dramatic accretion to light it up again. Its fate is a quiet one, a slow fading into cosmic night. V Sagittae's white dwarf, by contrast, is caught in one of the most violent and spectacular relationships imaginable, ensuring that its story will end with brilliance rather than silence. By understanding white dwarfs, we can see why V Sagittae's future is inevitable. These stars are compact, dense, and gravitationally powerful. Place one next to a donor star, and the stage is set for catastrophe. They are the remnants of death, yet paradoxically they often cause new explosions and flares when paired with another star. They are both endings and beginnings, the embers of stellar life and the triggers of new outbursts. V Sagittae's white dwarf embodies this duality perfectly, the dead core of a once shining star, now reborn as the engine of a future that will outshine the entire night sky. The heart of V Sagittae's unfolding drama lies in the moment when mass transfer begins. This is the cosmic theft that transforms an ordinary binary system into a ticking time bomb. Without this process, V Sagittae would be little more than a quiet pair of stars orbiting one another, destined to fade gently into obscurity. But with mass transfer, everything changes. It is here that the white dwarf reveals its true nature, not as a passive relic of stellar death, but as an active predator, siphoning the very life out of its companion. To understand how this happens, picture the gravitational tug-of-war that exists between the two stars. Both have their own gravity, and both exert influence on the space around them. Between them lies an invisible boundary, a kind of frontier, where their gravitational pulls balance. This boundary is known as the Roche lobe. As long as each star's material remains within its Roche lobe, it stays bound to that star. But V Sagittae's donor star has grown so large, and the two stars are so close, that its outer layers have spilled over this gravitational boundary. In other words, the donor can no longer hold on to all of its gas. The white dwarf, with its compact, voracious gravity, pulls that loose gas across the boundary, funneling it into its own domain. This is not a sudden tearing but a continuous, steady flow, like sand pouring through an hourglass. The donor star is literally bleeding mass, losing its outer layers in a stream that flows directly toward the white dwarf. To an observer nearby, this would not look like a gentle drift of gas but rather a torrent of material, rushing at speeds of hundreds of kilometers per second. The stolen gas doesn't land directly on the white dwarf surface. Instead, because of the orbital motion of the two stars, the gas spirals inward, creating a whirlpool of incandescent matter, the accretion disk. The beginning of mass transfer marks the moment when the system tips from balance into instability. The donor star is more massive than the white dwarf, and in most binaries, that fact would mean the donor remains in control. But because it has overfilled its Roche lobe, the donor is now at a disadvantage. As it loses material, it actually becomes less stable, causing it to expand further. Expansion means even more of its mass crosses the gravitational boundary, accelerating the transfer. This creates a runaway feedback loop. The more it loses, the more it has to lose. The more the white dwarf gains, the stronger its gravitational pull becomes. The scale of this transfer is staggering. Estimates suggest that V Sagittae's donor star is losing mass to its companion at a rate many thousands of times greater than in typical cataclysmic variable systems. To put it in human terms, it's as though a star was shedding the equivalent of an Earth's mass in gas every few weeks, streaming it toward the white dwarf. The sheer violence of this process explains why V Sagittae flickers and flares in brightness even now. We are already seeing the early signs of this theft in the light that reaches us. Mass transfer also explains why this system is destined to explode. A white dwarf is like a pressure cooker. It has no internal fusion of its own, but as gas piles up on its surface, it grows hotter and denser. Hydrogen accreted from the donor can ignite in violent bursts, leading to nova events. In most systems, these novae can repeat, blowing off some of the accreted matter and restoring a temporary balance. But in V Sagittae, the imbalance between the donor and the white dwarf is too extreme. The donor is too massive, the flow too great, and the white dwarf too overwhelmed. Instead of stabilizing, the system spirals toward a final eruption. For the donor star, this process is slow death. It is being cannibalized, drained of its outer layers by the relentless pull of its smaller but denser partner. With each passing orbit, it loses more of its mass and sinks deeper into instability. It is, in effect, being hollowed out by gravity. From Earth, we cannot see the gas streaming directly, but we can detect its consequences. The spectral fingerprints of heated hydrogen, the irregular brightening as fresh material slams into the accretion disk, the chaotic light variations that betray the violence occurring in that hidden corner of Sagitta. Mass transfer is not just an incidental detail, it is the central mechanism that seals V Sagittae's fate. Without it, the white dwarf would remain inert, cooling silently in space. Without it, the donor star might continue shining peacefully for millions of years. But because mass transfer has begun, the system has entered a phase of runaway evolution. It cannot go back. The gas will continue to flow, the white dwarf will continue to feed, and the instability will continue to build until the system reaches its catastrophic climax. There is something haunting about this process. It is not an explosion yet, not even a sudden crisis, but a slow and inevitable transfer of life from one star to another. A theft so complete that one star will eventually cease to exist, and the other will erupt in borrowed brilliance. In that sense, mass transfer is both a destructive act and the trigger for one of the most magnificent sights humanity will ever witness. V Sagittae's destiny begins here, with the slow siphoning of gas across an invisible boundary, a stream of matter that turns an ordinary binary into a cosmic countdown. When we picture a star stealing gas from its companion, it's easy to imagine that matter falling straight down onto the white dwarf, like water pouring into a basin. But the reality of how gravity and orbital motion interact is far more intricate, and far more spectacular. The stolen material doesn't simply plummet. Instead, it swirls into a great cosmic whirlpool, a glowing, spiraling structure known as an accretion disk. And in the case of V Sagittae, this disk is not just an incidental feature. It is the very engine of the system's chaos, the stage upon which the drama of its future explosion is being written. As the gas leaves the donor star and crosses the Roche-Lobe boundary, it carries with it the momentum of the orbital motion. This momentum prevents the gas from falling straight into the white dwarf. Instead, it arcs around, circling the dense core, spreading out and flattening into a disk. This accretion disk is made of superheated plasma, hydrogen and helium stripped of their electrons, spiraling inward at incredible speeds. Friction and compression heat the gas to astonishing temperatures, millions of degrees in the innermost regions. The result is a luminous, spinning structure that radiates across the spectrum, from visible light to X-rays. If we could stand close enough to witness it, the sight would be otherworldly. Imagine a blazing whirlpool of incandescent matter, glowing like a miniature galaxy, with streams of gas whipping around at thousands of kilometers per second. The disk would flare and shimmer, unstable and chaotic, as turbulence and magnetic fields churn the plasma into spirals and eddies. The innermost part of the disk would shine with searing intensity, while the outer regions glowed faintly, like embers cooling at the edges of a fire. The accretion disk is not merely decorative, it is where the violence of the system is converted into light. As gas spirals inward, gravitational energy is transformed into heat and radiation. Every particle of gas loses energy as it falls, releasing that energy as light. That is why V Sagittae appears brighter than it should for such a distant, faint system. We aren't just seeing starlight, we're seeing the glow of matter being shredded, compressed, and heated as it plunges toward the white dwarf. Accretion disks are common in astrophysics. They appear around young stars forming planets, around neutron stars, and around the supermassive black holes at the centers of galaxies. But in V Sagittae, the accretion disk has a particularly sinister role. It acts as a holding pen for the stolen gas, building up layers of hydrogen on the white dwarf surface. With each passing orbit, more gas piles up. Pressure increases. Temperature rises. And eventually, the conditions are right for runaway nuclear burning. This is the trigger for nova outbursts. But unlike most nova systems, where the process resets and repeats, V Sagittae's disk is feeding at such an unsustainable rate that the system cannot balance itself. The disk is overloading the white dwarf, driving it toward catastrophe. What makes the accretion disk even more fascinating is how unstable it is. Gas doesn't flow smoothly like water in a pipe. It clumps, it collides, it releases sudden bursts of energy. Astronomers observe this as flickering in V Sagittae's light, irregular changes in brightness that happen on timescales of minutes or hours. Each flicker is a reminder that we are watching a dynamic, volatile system, where immense energies are being released as streams of matter crash into the disk or spiral inward. These flickers are like the heartbeat of the system, revealing its restless nature. There's also the question of jets. In some accreting systems, the energy and magnetic fields in the disk focus some of the infalling matter into powerful beams that shoot outward into space at near-light speeds. These jets carve through the interstellar medium, announcing the system's violence across light years. In V Sagittae, it's possible that similar processes occur, though the details are still being studied. If jets are present, they would be another sign of the ferocity with which the disk channels gravitational energy into observable phenomena. From Earth, we cannot see the accretion disk directly. It is too far, too small, and too shrouded in distance. But we can infer its presence through spectroscopy. When astronomers split V Sagittae's light into its component wavelengths, they see the telltale emission lines of superheated hydrogen. These spectral fingerprints reveal gas moving at high velocities, heated to extraordinary temperatures, precisely the signature of an accretion disk. Even though our eyes cannot glimpse its structure, the data leaves no doubt. A glowing whirlpool of stolen matter surrounds the white dwarf, feeding it relentlessly. The accretion disk of V Sagittae is a paradoxical place. It is beautiful, a glowing, swirling ring of light suspended in the void. Yet it is also destructive, a mechanism of theft and instability. It is the channel through which the donor star's life is stripped away, atom by atom, orbit by orbit. Without the disk, the white dwarf would never gain the mass it needs to erupt. With the disk, the fate of the system is sealed. In a sense, the accretion disk is the visible manifestation of the relationship between the two stars. It is where the donor's sacrifice becomes the white dwarf's feast, where gravity's inexorable pull is converted into heat and light. And it is this very structure that makes V Sagittae flicker today and that will one day fuel its transformation into the brightest star in the sky. The whirlpool of matter circling the white dwarf is not just a side effect, it is the fuse, slowly burning, on the bomb that will detonate in 2083. The reason astronomers are so captivated by V Sagittae is not simply that it's a binary star system, or even that it has an accretion disk. What elevates this system from curiosity to cosmic spectacle is the way these processes combine to power events of staggering violence. To understand why V Sagittae matters, we must step back and look at what happens when a white dwarf receives stolen fuel from its companion. This mechanism, the steady siphoning of gas, its spiraling descent into the accretion disk, and its eventual piling up on the white dwarf surface, is the same engine behind some of the most brilliant fireworks the universe has to offer, novae and related explosive events. On its own, a white dwarf is inert. It has no fusion of its own to sustain, no internal power source, only the fading heat left over from its birth. But when new hydrogen from a companion begins to collect on its surface, the white dwarf essentially gets a second life. Layer after layer of this fresh fuel accumulates, compressed under the star's enormous gravity. Imagine pouring gasoline onto an ember that refuses to die. Each drop soaks in, and the ember glows hotter, until one day, it flares up in a sudden blaze. That is what happens on a cosmic scale when a white dwarf collects too much hydrogen. The gas builds up quietly at first, but as pressure mounts, the hydrogen at the base of the layer grows hotter and denser. Eventually, it reaches the critical conditions for nuclear fusion to ignite. But this ignition doesn't happen slowly, as in our sun's core. Instead, it ignites explosively, like a bomb. In a fraction of a second, the built-up hydrogen undergoes runaway nuclear burning, releasing an enormous amount of energy and blasting the outer layers of the white dwarf into space. This is what astronomers call a nova. The word comes from the Latin for new, because to early skywatchers, such explosions appeared as new stars suddenly flaring in the heavens before fading away. In many systems, novae repeat. The white dwarf gathers hydrogen, ignites it, blows it off, and then begins the cycle again. Each eruption is like a heartbeat, dramatic but survivable, allowing the system to continue its parasitic relationship for thousands or millions of years. But in V Sagittae, the rate of mass transfer is extreme. The donor star is pouring gas into the accretion disk at such a furious pace that the white dwarf cannot simply blow it off in small bursts. Instead, the system is building towards something far greater, a sustained runaway that will not settle into equilibrium. This is why astronomers pay such close attention. What normally produces novae is here pushed to an extraordinary, unprecedented extreme. The importance of this process goes far beyond spectacle. Novae and related stellar explosions play a fundamental role in the evolution of galaxies. When a white dwarf erupts, it doesn't just produce light, it ejects chemically enriched material into the cosmos. Elements forged in earlier nuclear burning, such as carbon, nitrogen, and oxygen, are blasted into interstellar space, where they seed the formation of new stars and planets. Without such processes, the universe would lack the raw ingredients for life. In this way, the violent cannibalism of systems like V Sagittae is directly tied to our own existence. The calcium in our bones, the oxygen we breathe, the iron in our blood, all of these elements were forged in stars and recycled through events like novae. But beyond the role of novae in cosmic recycling, the V Sagittae system offers us something rare: predictability. Normally, novae and supernovae strike without warning. Astronomers discover them only after they happen, scrambling to aim telescopes and gather data before the flare fades. With V Sagittae, the unfolding process of mass transfer and accretion allows scientists to forecast the coming outburst decades in advance. This is why the system matters so deeply. It is not just another nova waiting to happen. It is a cosmic event written into the future with enough certainty that humanity can prepare to witness it. The power source here, the mass transfer and accretion, matters because it is a universal mechanism. The same physics governs novae, supernovae, X-ray binaries, and even the feeding of black holes. By studying V Sagittae, astronomers are peering into a laboratory of extreme physics, where gravity, nuclear fusion, and quantum mechanics collide. Every flicker of light from the accretion disk, every spectral line from the infalling gas, teaches us something about how matter behaves under conditions we could never reproduce on Earth. And on a human level, why it matters is simple: we will get to see it. This mechanism, which usually plays out in the quiet anonymity of distant galaxies, is unfolding in our own Milky Way, close enough that when the final explosion comes, it will be visible to everyone on Earth without telescopes. The story of how stolen gas leads to stellar detonation is not just abstract astrophysics. It is the reason that, in 2083, people will step outside, look up, and see the night sky transformed. Children will ask why a new star burns brighter than Sirius or Venus, and the answer will be rooted in this very process: the slow, relentless siphoning of matter from one star to another, culminating in a blaze that will eclipse all other points of light. So, why does this matter? Because it connects us to the deep machinery of the cosmos. Because it explains how stars die, how elements are forged, how galaxies evolve, and how even destruction can give rise to beauty. And because, for perhaps the first time in history, we are not just witnesses stumbling upon a nova by chance, we are able to say with confidence that a star system will one day explode into brilliance, all because of the quiet but unstoppable process of mass transfer and accretion. Right now, if you went outside on the clearest of nights, under the darkest of skies, and gazed toward the constellation of Sagitta, you would not find V Sagittae with your unaided eyes. You could stand there for hours, scanning the stars, and all you would see are faint pinpricks of light making up one of the tiniest constellations in the sky. The star in question is simply too dim. Today, V Sagittae shines at around 10th magnitude, a level of brightness that lies far below the threshold of human vision. For context, the faintest stars visible to the naked eye under pristine, light pollution-free skies are about 6th magnitude. That means V Sagittae is at least 40 times fainter than the faintest star you could ever hope to see without help. To put this into perspective, astronomers use a logarithmic scale to measure brightness, where each step of 1 magnitude represents about a 2.5-fold change in brightness. A star at first magnitude is 2.5 times brighter than one at second magnitude, and so on. Sirius, the brightest star in the night sky today, blazes at about -1.5 magnitude. Venus, when it shines as an evening star, can reach about -4 magnitude. And the full moon overwhelms everything at around -12.7 magnitude. V Sagittae, sitting at +10, is so faint that even backyard stargazers with modest telescopes need to know exactly where to look, guided by star charts, to even confirm its existence. What's striking about this faintness is how completely ordinary it seems. 4 centuries after its discovery, V Sagittae was just another dim, forgettable speck catalogued among countless others. Nothing about it suggested the spectacular fate awaiting it. It is humbling to think that a system destined to one day outshine every star in the sky currently hides in plain sight, invisible to all but the patient observer with a telescope. The future brightest star is, at this very moment, one of the most unremarkable points in the heavens. Astronomers know V Sagittae is faint not only by direct observation but also by studying its fluctuating light. This star does not shine steadily. It flickers, waxes, and wanes, sometimes growing slightly brighter, sometimes dimmer. These variations are signatures of the chaotic mass transfer and accretion happening inside the system. Even though the system is faint overall, its flickering is detectable in the data, a kind of heartbeat betraying its turbulent nature. If you could amplify the light curve and watch it in real time, you'd see it jitter and dance in brightness, small ripples that tell us we're looking at a restless and unstable pair of stars. The faintness of V Sagittae also speaks to its distance. Located roughly 7,800 light-years away, this system is not exactly in our galactic backyard. Though that distance is modest by the standards of the Milky Way, it's enough to make a faint system nearly invisible to us. At such distances, only intrinsically luminous stars, giants, supergiants, or those in violent outburst, stand out clearly. A quiet binary system with modest light output simply sinks into obscurity. This makes it all the more extraordinary that one day, despite this distance, V Sagittae will blaze bright enough to rival the moon. The contrast between its faint present and its blazing future could not be starker. For astronomers, V Sagittae's current faintness is both a challenge and a gift. The challenge lies in studying something so dim. It requires sensitive instruments, careful data collection, and patient observation over decades. But the gift is that we can watch it change, incrementally, as mass transfer intensifies and the system inches toward catastrophe. When compared with older data from photographic plates and early telescopic records, scientists can actually measure the acceleration of mass transfer, the deepening instability, and the gradual shift in the system's brightness over time. These subtle changes, detectable only through dedicated study, are what allowed astronomers to predict the system's fate in the first place. What's fascinating is how this faintness hides a paradox. To our eyes, V Sagittae seems insignificant, but its internal processes are anything but. The white dwarf and its companion are locked in a struggle of gravity and survival, with torrents of gas flowing from one to the other. If we could magnify our vision, zooming past the faint point of light we register through a telescope, we would see streams of incandescent plasma spiraling into a glowing accretion disk, heated to millions of degrees. We would see violence and energy on a scale far beyond human comprehension, all masquerading as a tiny, almost invisible star. It's almost poetic. The star system destined for unparalleled brilliance is, today, barely visible at all. It reminds us that appearances in the cosmos can be deceiving. The faintest spark may one day become a beacon, and the most ordinary point of light may hide a story of immense drama. In 2083, people will look up at the sky and see a new star brighter than Sirius or Venus, and yet that star was there all along, hiding in obscurity. V Sagittae, at 10th magnitude today, is proof that the universe holds secrets in plain sight, waiting for the right moment to reveal their true nature. The story of V Sagittae's impending eruption is, at its core, a story of imbalance. Binary star systems can sometimes live in a kind of harmony, with each partner minding its own gravitational space, orbiting quietly for millions, even billions, of years. But V Sagittae is different. It is a relationship gone wrong, a pairing so mismatched in mass and structure that it has entered a runaway spiral of instability. The mass ratio between the donor star and the white dwarf companion is the key to understanding why this system cannot survive in its present state and why it is doomed to flare into a cosmic spectacle. In most binary systems that feature a white dwarf and a donor star, the donor is the smaller partner. A star less massive than the Sun, perhaps a red dwarf or a Sun-like star, slowly transfers some of its outer layers into the gravitational well of the white dwarf. The flow may be steady but relatively modest, allowing the system to find an uneasy balance. In such cases, the white dwarf feeds, erupts occasionally in nova events, but overall, the mass transfer can remain sustainable for a long period. But in V Sagittae, the situation is reversed. The donor star is more massive than the white dwarf. By some estimates, the donor weighs in at nearly 4 times the Sun's mass, while the white dwarf is closer to 1 solar mass. That means the donor star is not a fragile companion but a heavyweight, forced into an orbit so close that it is being stripped of its life. This reversal of roles creates a catastrophic instability. Why is this so important? In binary dynamics, the stability of mass transfer depends heavily on the ratio of the two masses. When the donor is lighter, the transfer process can stabilize. Mass loss causes the donor to shrink, which can reduce overflow and ease the flow of gas. But when the donor is heavier, the opposite happens. As it loses mass, it does not shrink enough to restore balance. Instead, it expands, spilling even more of its material beyond its Roche lobe. This creates a feedback loop. The more mass the donor loses, the more unstable the process becomes, and the faster it loses mass. It is a self-reinforcing cycle with no escape route. The imbalance also amplifies the violence of the transfer. The white dwarf, despite being less massive, is infinitely denser, with its gravity concentrated into a tiny Earth-sized sphere. It exerts an irresistible pull on any gas that strays beyond the Roche lobe. And because the donor star is so much heavier, it has a vast reservoir of material to give. The result is a torrent rather than a trickle, an overwhelming flood of gas being funneled into the accretion disk. The accretion rate here is among the highest ever recorded in such systems, far exceeding the gentle feeding seen in more balanced binaries. Think of it like a cosmic seesaw that has tipped far to one side. The heavy donor star tries to maintain its form, but with each loss of material, it leans further out of balance. The white dwarf, though smaller, has positioned itself perfectly to exploit this imbalance, pulling harder and harder as the donor grows weaker. The system as a whole spirals further into instability, with no mechanism to return to equilibrium. Astronomers studying V Sagittae have noted that this runaway mass ratio makes it unique. In nearly all known cataclysmic variable stars, the donor is the lightweight. Here, the heavyweight donor star is being consumed by a partner that should, by all accounts, be the weaker member. It is a cosmic irony. The larger star, usually the dominant figure in stellar relationships, is being devoured by something far smaller in size but infinitely denser in gravity. This imbalance also determines the timeline. If the donor were lighter, the system might last millions of years before reaching a catastrophic point. But because the donor is massive, the runaway process unfolds on human timescales, mere decades rather than eons. That is why scientists can predict V Sagittae's eruption within this century, around 2083. The imbalance has accelerated the process beyond the usual slow grind of stellar evolution, speeding it toward a finale we can actually witness. From Earth, we can already see the signs of this imbalance in the system's erratic light. The flickering brightness, the irregular variations, the strange spectral signatures, all of them are echoes of the unstable mass transfer at work. The imbalance has made the donor star puffier, more unstable, more prone to spilling its gas. The white dwarf, meanwhile, is becoming overloaded with more material than it can process. Each orbit tightens the grip, each transfer destabilizes the donor further. It is almost like watching a predator and prey lock together, with the prey much larger in size but bleeding out faster and faster, and the predator feeding more frantically with every moment. In this deadly embrace, size is not strength. Density and gravity win. And in the end, the imbalance ensures there will be no survivors as they exist today. The donor will be stripped to nothing, and the white dwarf will be pushed to erupt in a brilliance that will momentarily rewrite the night sky. This growing imbalance is the reason V Sagittae cannot be just another flickering binary. It is why astronomers are so certain that the system will not quietly settle down, but instead build toward a runaway event. The imbalance is not just a quirk, it is the fuse on the cosmic firework, shortening with every passing year. The word runaway in astronomy carries a special weight. It doesn't mean merely fast or chaotic, it describes a process that feeds on itself, a chain reaction with no natural stopping point, something that accelerates until it reaches a dramatic, often catastrophic conclusion. In the case of V Sagittae, the runaway process is the culmination of everything we have described so far: the extreme closeness of the stars, the overwhelming imbalance of their masses, and the relentless flow of material from the donor to the white dwarf. What begins as a steady siphoning of gas soon turns into an uncontrollable frenzy, a cosmic cascade that will not end until the system erupts in blinding brilliance. At the heart of this runaway lies feedback. The donor star, more massive than the white dwarf, should by all logic be the dominant partner. But because of the tight orbit and the Roche lobe overflow, its mass is being stripped away at an unsustainable pace. Each bit of gas it loses makes it less able to contain the rest of its envelope. Instead of shrinking back within its Roche lobe and stabilizing, as smaller donor stars often do, this one swells outward. The expansion only increases the overflow. So, the more mass it loses, the more mass it is forced to lose. It's like a wound that refuses to clot, bleeding faster the longer it goes on. For the white dwarf, this is an opportunity, and a problem. As torrents of hydrogen and helium stream across space, they spiral into the accretion disk and crash onto its surface. The white dwarf's gravity is immense, and the material slams into it at thousands of kilometers per second, releasing staggering amounts of energy as heat and light. But the white dwarf has no way to stop the inflow. It cannot refuse the donation. It cannot spit it back out in a controlled way. The gas keeps coming, faster and faster, and the white dwarf is forced to absorb it. This accelerates the feeding process. The more gas arrives, the hotter the white dwarf becomes. The hotter it becomes, the more violently it interacts with new gas, causing turbulence in the accretion disk and creating even more flickering and instability. From Earth, this is visible as irregular surges in brightness, the telltale signs of a system spinning out of control. The white dwarf is, in a sense, choking on the very fuel it craves, swallowing more and more, faster than it can manage, until the process tips into runaway. The mathematics of this are well understood. The accretion rate in V Sagittae is not like the trickle of most cataclysmic variables. It is a flood. Astronomers calculate that the white dwarf is gathering material at rates thousands of times higher than those of typical nova systems. Imagine trying to drink from a fire hose. At first, you might manage a few gulps, but soon the sheer volume overwhelms you. That is what the white dwarf is experiencing, not a sustainable flow, but an accelerating torrent that grows stronger with every orbit. This runaway process is what guarantees V Sagittae's dramatic fate. In most systems, novae occur because accretion slows down enough to allow hydrogen to accumulate, ignite, and blow off in bursts, repeating the cycle. But in this case, the transfer is so extreme that the system cannot reset. The white dwarf doesn't have time to recover. It is being force-fed to the point of collapse. Every drop of gas that falls onto its surface increases the pressure at the base of the accreted layer. Every increase in pressure brings the system closer to ignition, not of a modest nova, but of a runaway conflagration. And it is not only the white dwarf that spirals into crisis. The donor star, destabilized by its rapid mass loss, grows puffier and more unstable. This puffiness ensures that even more of its material spills across the Roche lobe, further accelerating the mass transfer. The two stars are locked in a vicious cycle. The donor star loses mass, which makes it less stable, which makes it lose mass even faster. The white dwarf gains mass, which makes it hotter and more unstable, which makes it absorb gas even more efficiently. Together, they have entered a downward spiral with no off-ramp. If we could zoom into the system and watch the process unfold, we would see a luminous whirlpool of gas glowing brighter with each passing day, streams of plasma whipping across space, the donor star visibly distorted into a teardrop shape as it is siphoned away. The white dwarf surface would be a seething cauldron, layers of hydrogen and helium piling up, squeezed under unimaginable gravity. To our eyes, it would be a scene of unrelenting chaos, but to an astronomer, it would be the clearest sign of runaway evolution, a process destined to climax not in silence but in a flood of light. This runaway is what sets the clock ticking toward 2083. Astronomers can calculate how quickly mass is being transferred, how unstable the donor has become, and how much material the white dwarf can absorb before the inevitable ignition. The equations show that the system has entered a phase where the feeding rate will only accelerate, tightening the timeline. We are not talking about millions of years. We are not even talking about thousands. The runaway will reach its climax within the span of a human lifetime. What makes this even more extraordinary is that we are alive during the final approach. For billions of years, the system maintained some semblance of balance. For centuries, it glowed faintly, unnoticed by the human eye. But now, in our time, the runaway has begun in earnest. We are the first generation to see the flickers that betray its growing instability, and future generations will be the ones to witness the dazzling finale. The runaway process is not theoretical, it is observable, measurable, and inexorable. In essence, the white dwarf has become a predator that cannot stop feeding, a fire that grows hotter the more fuel it consumes, a chain reaction racing toward its conclusion. The runaway ensures that V Sagittae is not just another faint star in the catalogue but the centerpiece of one of the greatest astronomical events in human history. The runaway feeding of V Sagittae will not continue forever. Every accelerating process in the cosmos eventually meets a threshold, a point of no return where the system cannot adjust, cannot slow down, cannot find balance. For V Sagittae, this inevitable threshold is what astronomers call the tipping point. It is the stage where the donor star has given up so much of its mass and the white dwarf has absorbed so much fuel that the entire binary can no longer function as it has for thousands of years. The tipping point is not merely a phase, it is the moment that transforms a faint, overlooked star into the brightest object in Earth's night sky. The first part of this tipping point involves the donor star. At present, it is far larger and more massive than the white dwarf. But with every orbit, with every cycle of mass transfer, it is being whittled down. The star is bleeding material at an extraordinary rate, its outer layers pulled inexorably into the accretion disk and consumed. As it loses mass, it becomes progressively less stable. Instead of shrinking and contracting into a tighter, more manageable form, as a smaller donor might do, it swells outward, becoming more distended. This swelling guarantees that even more of its material spills into the gravitational grasp of the white dwarf. It is a vicious circle. The less mass it retains, the more quickly it loses what remains. At some point, the donor star will be reduced to a mere shell of its former self. Its structure will be so distorted, so weakened by constant mass loss, that it can no longer sustain its identity as a functioning star. It will be little more than a bloated husk, unable to resist the white dwarf's hunger. When this moment arrives, the system will be irrevocably destabilized. The donor will essentially be consumed in the gravitational and thermonuclear grip of its companion. The second part of the tipping point concerns the white dwarf itself. White dwarfs, despite their small size, are extraordinary in their ability to store energy in the form of accreted material. Every atom that falls onto their surface is compressed under colossal pressure. Hydrogen, the most abundant element being transferred, does not simply rest quietly. It piles up layer upon layer, growing hotter and more pressurized until it reaches the conditions necessary for nuclear fusion. Ordinarily, in novae, these fusions happen in bursts. A modest amount of hydrogen ignites, blows off into space, and the cycle starts over. But V Sagittae is different. The accretion rate is so extreme that the white dwarf is unable to relieve itself in small eruptions. It is swallowing too much, too quickly. As this continues, the base of the accreted layer becomes a ticking bomb. Pressures climb to levels unimaginable on Earth, temperatures rise into the tens of millions of degrees, and the hydrogen layer becomes primed for runaway nuclear ignition. When the donor star reaches the end of its life and pours the last of its mass onto the white dwarf, the pressure cooker will finally blow. Astronomers predict that at this tipping point, the white dwarf will unleash its stored energy in a cataclysmic explosion of light and radiation. What makes the tipping point so dramatic is that it will be sudden. To human eyes, the system will appear faint and unremarkable for decades. There may be small flickers, slight increases in brightness as instability grows, but the real change will come swiftly. Within a matter of days, or perhaps even hours, the system will surge from invisibility to overwhelming brilliance. A star you cannot see even with binoculars today will erupt into a beacon rivaling the full moon. It is a cosmic switch, flipped when the donor star is fully consumed and the white dwarf can no longer contain the nuclear fire within. This moment is what astronomers have zeroed in on with their predictions. By modeling the current rate of mass transfer, the instability of the donor, and the white dwarf's accumulation of material, they estimate that the tipping point will occur around the year 2083. The calculations are not exact. Such events are notoriously hard to pin down, but the fact that they can predict a window at all is astounding. It means that humanity is not just waiting for a random nova or supernova to occur. We are counting down to a specific, observable event that has already begun its final act. When the tipping point arrives, it will not be subtle. The night sky will transform. Even those who know nothing of astronomy will look up and see a new, brilliant light, shining where none had been before. For weeks or months, the world will be captivated, reminded that the universe is not static but alive with forces so vast that they dwarf everything we know. And behind the beauty of that light show will be the tragic finale of a stellar partnership that spiraled out of control. The donor star devoured, the white dwarf erupting, the balance broken forever. The tipping point of V Sagittae is not just a prediction of brightness. It is a rare opportunity for astronomers to watch, in real time, the endgame of a binary system collapsing under its own imbalance. It is the moment where theory becomes spectacle, where numbers on a page become a light in the sky so bright it casts shadows on the ground. And the fact that we know this moment is coming is what makes V Sagittae one of the most extraordinary stories in all of astronomy. As the years progress toward 2083, the tension within V Sagittae will become almost unbearable in cosmic terms. For centuries, it has been quietly siphoning matter, each orbit transferring gas from the massive donor to the compact, insatiable white dwarf. Over time, this dance has intensified, the donor star swelling and destabilizing, the white dwarf, accumulating an impossible load of material. And then, in a relatively short span, the system will reach its ultimate crescendo, the great outburst. This is not a flicker, not a modest flare like a typical nova, but a cataclysmic surge in luminosity that will transform the night sky as humanity has never seen it before. The build-up to this explosion is driven by the runaway process we have described. By the early 2080s, the donor star will have lost an overwhelming portion of its mass. Its outer layers, stretched and distorted by the immense gravitational pull of the white dwarf, will be feeding into the accretion disk at rates higher than ever before. Each orbit increases the pressure on the white dwarf surface. The accumulated hydrogen and helium, compressed by immense gravity, has reached temperatures and densities sufficient to trigger an uncontrollable nuclear reaction. This is the tipping point made manifest. The white dwarf is no longer simply burning fuel. It is primed to release the full extent of its stored energy in a single, dramatic event. Observers of the night sky in 2083 will witness a star system that, until recently, was invisible to the naked eye, suddenly flaring to brilliance. For decades, it has been at 10th magnitude, hidden in the tiny constellation of Sagitta, quietly undergoing catastrophic internal changes. Then, over a period of days or weeks, it will rise to become one of the brightest objects in the sky, surpassing even Sirius, the brightest star in our current heavens. The light from V Sagittae will be impossible to ignore, drawing the eyes of casual stargazers, photographers, and professional astronomers alike. The physics behind this outburst is staggering. The white dwarf, now carrying a massive envelope of freshly accreted gas, experiences nuclear ignition in an uncontrollable, explosive manner. Temperatures soar, hydrogen fusion races across its surface, and energy is released at a rate that dwarfs the combined output of millions of suns for the brief duration of the event. This energy drives the expansion of the outer layers, propelling them into space at tremendous speeds, producing a luminous shell that radiates across the electromagnetic spectrum. It is, in essence, a nova on steroids, a superbright stellar flare visible across vast distances. Unlike typical novae, which reach their peak and fade over days to weeks, the great outburst of V Sagittae will be sustained for a much longer period. Models suggest that it will maintain extreme brightness for several weeks and perhaps even months. The initial surge will be almost blinding compared to the faint star we see today, gradually tapering as the outer layers are expelled and the nuclear reaction subsides. During this period, the light of V Sagittae may rival the moon's glow, casting shadows at night and transforming familiar constellations into a backdrop for this cosmic spectacle. The anticipation among astronomers is intense. Because this event has been predicted decades in advance, telescopes, both on the ground and in orbit, will be pointed towards Sagitta long before the peak. Instruments sensitive to X-rays, ultraviolet, infrared, and radio waves will capture every nuance of the explosion. Scientists will watch the evolution of the accretion disk, the behavior of the ejected material, and the nuclear reactions on the white dwarf surface. The data will provide unprecedented insights into the physics of binary interactions, runaway mass transfer, and extreme stellar explosions. For casual observers, the experience will be equally remarkable. Those standing outside at night will see a star that seems impossibly bright, lighting up the sky in a way no one alive today has ever witnessed. Its position in Sagitta will be unmistakable, a point of dazzling radiance where once there was only darkness. Unlike most novae or supernovae, which occur in distant galaxies and appear as faint smudges even through telescopes, V Sagittae's outburst will be a luminous jewel within our own Milky Way, visible to anyone with clear skies and a sense of wonder. There is also a sense of cosmic irony in this event. For centuries, V Sagittae has been a dim, unassuming point of light, catalogued and largely ignored. Its existence has gone unnoticed by casual stargazers, invisible without a telescope. Yet, by 2083, this same star system, which once barely registered at 10th magnitude, will dominate the night sky. The contrast between its current invisibility and its future brilliance underscores the unpredictability and drama inherent in the universe. What seems ordinary today can become extraordinary tomorrow. The Great Outburst will mark not only the climax of V Sagittae's story but also the culmination of a series of astronomical observations and predictions that have spanned decades. Scientists will finally see the results of their models, confirming decades of work on binary star evolution, mass transfer, and accretion physics. The data collected during the event will be invaluable for understanding the life cycles of stars, the dynamics of white dwarfs, and the conditions that lead to extreme stellar eruptions. In the context of human experience, the timing of this outburst is staggering. It is rare, perhaps unprecedented, that a celestial event of this magnitude has been predicted with enough certainty that a generation of observers can prepare to witness it. For many people, it will be a once-in-a-lifetime experience, an opportunity to see a star rise to unprecedented brightness in real time. The spectacle will be visible worldwide, transcending borders, cultures, and languages. A shared moment of wonder, tied directly to the physics unfolding in a distant corner of our galaxy. The Great Outburst is the moment when theory becomes reality. All of the processes we have traced, the donor star's instability, the runaway mass transfer, the accumulation of hydrogen on the white dwarf, the formation of the accretion disk, and the accelerating imbalance between the stars, will culminate in a display of sheer cosmic power. In an instant, V Sagittae will assert itself as a dominant presence in our skies, a luminous reminder of the forces shaping the universe and of humanity's unique position as observers capable of predicting and witnessing such phenomena. When astronomers speak of the brightness of stars, they are talking in terms of apparent magnitude, a scale that measures how bright a celestial object appears from Earth. The scale is logarithmic. Smaller numbers correspond to brighter objects, and negative numbers indicate extreme brilliance. For context, Sirius, the brightest star in our current night sky, shines at about -1.5 magnitude. Venus, when it reaches peak visibility as an evening or morning star, can reach -4 magnitude, dazzling the eye as it reflects sunlight. And the full moon, an object whose light dominates the night sky, registers around -12.7 magnitude. These are the benchmarks by which we measure extraordinary brightness. V Sagittae, at the moment of its great outburst in 2083, is predicted to exceed all of these standards. Based on detailed modeling of the mass transfer rate, the white dwarf's accumulated fuel, and the eventual thermonuclear explosion, astronomers estimate that V Sagittae could reach -7 magnitude or even brighter. To put this in perspective, a -7 magnitude object would outshine Sirius by a factor of about 25 and Venus by more than 10 times. It would be luminous enough to cast faint shadows at night, a level of brightness nearly rivaling the full moon. For a star that today is completely invisible to the naked eye at 10th magnitude, this represents a transformation of more than 40,000 times its current luminosity. This predicted magnitude is not just a theoretical number. It arises from precise calculations of the mass of the white dwarf, the rate of gas accumulation, the efficiency of nuclear fusion, and the energy released during the eruption. Astrophysicists have studied V Sagittae for decades, observing the flickering of its accretion disk, measuring spectral lines from the transferred gas, and modeling how the runaway nuclear burning will proceed once the tipping point is reached. All evidence points toward a spectacular, sudden release of energy that will elevate the system from obscurity to one of the brightest points in the night sky. The implications for observers on Earth are staggering. Imagine stepping outside one evening, scanning the familiar stars of the northern summer sky, and suddenly noticing a point of light more brilliant than any star you have ever seen. Its glow would dominate the sky in the small constellation of Sagitta, a constellation so tiny that it is often overlooked. Its position near the zenith of summer for observers in the northern hemisphere would make it easy to locate. Unlike transient novae that appear in distant galaxies as faint smudges, V Sagittae's light would be unmistakable, bright enough to draw the attention of anyone who gazes upward. Because of its extreme brightness, V Sagittae will become a celestial landmark. Amateur astronomers will point telescopes at it for months, capturing its fluctuations and the expansion of the ejected material. Professional observatories and space telescopes will monitor it continuously across multiple wavelengths, from visible light to X-rays and radio waves, documenting the progression of the explosion in unprecedented detail. Scientists will watch as the energy from the white dwarf spreads outward, lighting up surrounding gas and dust, providing real-time insights into the physics of extreme stellar events. What makes this magnitude so remarkable is that it transforms V Sagittae into a global phenomenon. Unlike other stellar eruptions, which might be visible only with telescopes or under dark skies, V Sagittae's brilliance will be apparent to the naked eye worldwide. People in cities, villages, deserts, and mountains alike will all witness it. Even in areas with moderate light pollution, the star's light will dominate the night sky. It will be the first nova-like explosion in human history predicted well enough in advance that observers can prepare for its peak, ensuring that humanity experiences a truly synchronized cosmic event. The predicted magnitude also reinforces the uniqueness of V Sagittae's outburst. While many stars undergo nova explosions, most are far too distant or faint to be spectacular to the human eye. Supernovae in nearby galaxies can rival brightness temporarily but remain largely invisible to casual observers. V Sagittae, however, is in our own galaxy, close enough that its outburst will be transformative. Its light will not be a mere point among countless stars, it will dominate the entire landscape of the night sky, eclipsing even the most celebrated celestial objects currently visible. The sheer scale of this brightness underscores the power of the runaway process we have described. A star that today is dim, unremarkable, and barely detectable, will in 2083 shine with unprecedented intensity, the product of billions of years of stellar evolution, decades of mass transfer, and the explosive ignition of nuclear fuel compressed on a white dwarf surface. It will serve as a dramatic reminder of the hidden energies and dynamics of our galaxy, the immense forces that govern the lives and deaths of stars, and humanity's ability to anticipate and understand them. For the casual observer, this magnitude will be shocking. People accustomed to the familiar brilliance of Venus, the glow of Sirius, or the majesty of the full moon will find that V Sagittae surpasses them all, becoming a point of awe and wonder. Its brightness will not only illuminate the night sky but also the human imagination, inspiring stories, scientific inquiry, and a sense of connection to the vast, dynamic cosmos. When V Sagittae reaches its climactic brilliance, it will no longer be the hidden, faint star catalogued at 10th magnitude. Instead, it will become a cosmic spectacle visible across the entire globe, a rare event that transcends geographical boundaries, urban light pollution, and even the limitations of human vision. Its light will shine so powerfully that observers on every continent, from bustling cities to remote wildernesses, will be able to witness it without the aid of telescopes, binoculars, or specialized equipment. The entire world, regardless of latitude or culture, will share in the awe-inspiring experience of seeing a new star emerge brighter than any other celestial object in the night sky. Because of its location in the small constellation of Sagitta, V Sagittae will be most prominent for observers in the northern hemisphere, especially during summer months when Sagitta sits high overhead. Yet its brilliance is such that even observers closer to the equator, or in parts of the southern hemisphere, will not miss it entirely. Its apparent magnitude, predicted to reach -7 or brighter, ensures that it will pierce through the night sky with enough luminosity to stand out against the backdrop of city lights and atmospheric scattering. Unlike ordinary stars that require darkness and patience to spot, V Sagittae will assert itself immediately, visible as a bright, steady point of light that dominates the heavens. The worldwide visibility of V Sagittae is unprecedented in human experience. While we occasionally witness supernovae in other galaxies, or brilliant meteor showers, these events are often subtle, distant, or fleeting. Even the brightest supernovae are generally visible only through telescopes. V Sagittae, in contrast, will be bright enough to cast shadows, temporarily rivaling the moon in illumination. People will be able to step outside at night, look towards Sagitta, and see a star that seems impossibly large, impossibly bright, and impossibly close, all within their own lifetime. It is a celestial event that requires no equipment, no expertise, no astrophotography, merely the ability to look upward and be struck by wonder. For astronomers, this worldwide visibility is a boon. Citizen scientists and amateur stargazers around the globe will contribute observations, measurements, and photographs, creating a vast network of data points from different latitudes and longitudes. Observatories can compare these reports with high-resolution telescope data to track subtle variations in brightness, the expansion of ejected material, and other transient phenomena. The universality of visibility ensures that V Sagittae will not be studied solely by professionals. It will engage the global public in real-time astronomy on an extraordinary scale, something few other stellar events have ever achieved. There is also a symbolic aspect to this global visibility. For the first time in recorded human history, we may witness a stellar explosion whose timing has been predicted decades in advance, visible simultaneously from nearly every corner of the Earth. It will become a shared cultural and scientific event, sparking curiosity, conversation, and/or across nations. Children in Africa, astronomers in Europe, hikers in South America, or city dwellers in Asia will all look up and see the same star dominating the sky, linking humanity through a shared experience of cosmic scale. The fact that V Sagittae will be visible without telescopes is also a reminder of the accessibility of the universe. Humanity often relies on instruments to witness celestial phenomena, space telescopes, large observatories, or high-powered amateur telescopes. But here is a star that, despite being nearly 7,800 light-years away, will shine so brightly that no tools are needed. Anyone with a clear view of the night sky will experience it firsthand. Its light will reach Earth as a direct connection to cosmic processes unfolding over decades, a story written in hydrogen, gravity, and nuclear energy, visible to all without intermediaries. The worldwide impact will also be educational. Schools and science centers can use the event as a real-life teaching moment. For astronomy enthusiasts, it is a rare chance to observe the unfolding stages of a nova-like eruption in real time. The star will be bright enough that even casual observation, made with simple notes, sketches, or photographs, can contribute to a broader understanding of stellar physics. The accessibility of this phenomenon turns it into a global classroom, where anyone with curiosity and a clear sky can become part of the story. Furthermore, the visibility of V Sagittae will persist for weeks, possibly months, meaning the world will not experience it as a fleeting, once-in-an-instant flash, but as a prolonged event that allows multiple generations to witness and document it. Families will step outside on consecutive evenings, tracking the gradual rise, peak, and eventual decline of its brightness. Societies around the globe will share the collective memory of seeing a star blaze brighter than Venus or Sirius, a rare phenomenon that has only been glimpsed from Earth in the distant past, often unpredictably. The universality of visibility also emphasizes the scale of the cosmic forces at play. Here is a star system that, until recently, was hidden and unremarkable, now asserting itself with such brilliance that it dominates the entire night sky. The sheer power required for a star thousands of light-years away to outshine every other star visible from Earth is immense, a testament to the energy released by the runaway mass transfer, the accretion onto the white dwarf, and the ensuing thermonuclear explosion. It is a reminder that the universe is not static. The heavens can erupt, transform, and astonish without warning, or, in the case of V Sagittae, according to predictions made decades in advance. In summary, the visibility of V Sagittae worldwide is unprecedented and transformative. It will unite observers across continents, urban and rural alike, under a single, brilliant point of light. Its naked-eye visibility ensures that it will become a shared experience for humanity, a reminder of the cosmic forces at work in our galaxy, and a spectacle that requires nothing more than attention and awe. For those who witness it, the night sky will never feel ordinary again. Once V Sagittae erupts in its great outburst, one of the most remarkable aspects of the event will be the duration of its brilliance. Unlike transient meteors, fleeting flares, or most supernovae, which peak and fade quickly, the V Sagittae explosion is predicted to remain conspicuously bright for weeks and possibly even months, offering humanity an unprecedented opportunity to witness a stellar spectacle unfold over an extended period. This prolonged luminosity is not a coincidence. It is the natural outcome of the system's extreme mass transfer, accretion, and runaway nuclear burning processes, combined with the physics of the white dwarf and the donor star. The key factor determining the duration of V Sagittae's brightness is the enormous amount of material that the white dwarf will have accumulated before the tipping point. Over decades of steady siphoning from its companion, the white dwarf will acquire a thick, dense envelope of hydrogen and helium. When nuclear fusion ignites in a runaway fashion, this massive reservoir will burn explosively, but the reaction will take time to fully propagate through the layers of accumulated gas. Unlike smaller nova events, where a thin layer burns quickly and is expelled in a matter of days, V Sagittae's fuel mass is substantial, providing a sustained energy output that will maintain extreme brightness for an extended interval. The mechanics of this sustained luminosity are fascinating. As nuclear fusion spreads across the surface of the white dwarf, it drives the expansion of the outer layers, creating a glowing shell of ejected material. This shell is heated by both the nuclear energy released and the kinetic energy of expansion, causing it to radiate intensely across the electromagnetic spectrum. Initially, the energy is concentrated, producing the dazzling peak visible to observers worldwide. As the shell expands and cools, the brightness will gradually decrease, but the process is slow. The immense mass and density of the material ensure that this cooling, and thus the fading of the light, takes place over weeks or months, not mere hours. During this period, the light of V Sagittae will remain extraordinary. At its peak, it may rival the brightness of the full moon, casting shadows and dominating the night sky. Over the following days and weeks, even as it gradually dims, it will still outshine Sirius, Venus, and nearly every other star. This slow decline will allow astronomers to study the dynamics of the explosion in remarkable detail. They will observe the behavior of the ejected shell, track changes in brightness, and gather spectra that reveal the chemical composition of the expelled material. The extended visibility transforms what could have been a brief, ephemeral event into a cosmic laboratory, offering a rare window into the physics of stellar death and explosive nucleosynthesis. For casual observers, the extended brightness is equally significant. Most people will not need to wake in the dead of night or camp under perfect conditions to witness the peak. The weeks-long duration means that families, school children, amateur astronomers, and global audiences will have multiple opportunities to observe the event, compare notes, and marvel at the changing night sky. In essence, V Sagittae will become a persistent fixture in the heavens, a prolonged show that draws the attention of the world not just once but repeatedly, night after night. The duration of the event also enhances its cultural and psychological impact. Unlike a brief flare that might go unnoticed or be easily forgotten, a weeks- or months-long phenomenon allows societies around the globe to integrate it into human memory and lore. Observers will document its rise and fall, take photographs, and write descriptions, ensuring that future generations have a detailed record of what was seen. This extended timescale will allow humanity to collectively appreciate the mechanics of a runaway stellar system, the physics of accretion and nuclear fusion, and the sheer magnitude of energy involved in such an explosion. Moreover, the extended visibility is a testament to the power of the runaway process that drives V Sagittae. The system is not merely producing a quick flare, it is releasing the energy accumulated over decades of mass transfer in a controlled yet extraordinarily intense manner. Each moment of light we see is a result of both the original hydrogen from the donor star and the intricate interplay of gravity, nuclear fusion, and thermodynamics. The weeks-long brilliance is effectively the white dwarf and donor star's final performance, a prolonged release of the energy stored during their violent cosmic relationship. It is also worth noting that the long duration allows for variability within the brightness itself. Astronomers anticipate that the light curve of V Sagittae will not be perfectly smooth. There may be short-term fluctuations, small dips and rises, caused by instabilities in the ejected shell, interactions with remaining accretion disk material, or complex nuclear burning processes. For observers on Earth, this means the event will feel dynamic, alive, and unpredictable, even as it maintains a level of overall brilliance. Each night, the sky may appear subtly different, reflecting the ongoing evolution of the explosion. Finally, the prolonged shine of V Sagittae emphasizes the rarity and significance of the event. Few stellar phenomena are both predictable and extended. Most novae are sudden, brief, and often invisible to casual observers. Supernovae, while spectacular, are generally distant and fleeting. V Sagittae, in contrast, combines predictability, proximity, extraordinary brightness, and duration, making it a once-in-a-lifetime spectacle that humanity can fully witness. For weeks or months, the star will dominate the night sky, providing both a scientific treasure trove and a source of wonder accessible to all who look upward. When considering V Sagittae's impending outburst, it's useful to place it within the broader context of historical stellar explosions, particularly other novae and luminous events that have temporarily transformed the night sky. While V Sagittae promises unprecedented brilliance and predictability, its behavior resonates with patterns observed in earlier cosmic fireworks, offering both a sense of continuity and a striking contrast with the stars of the past. One of the most famous examples of a nova is Nova Cygni 1670, also known historically as CK Vulpeculae. This eruption, observed in the 17th century, shocked early astronomers and skywatchers because a previously invisible star suddenly appeared as a bright, fluctuating point of light. It rose in luminosity over weeks, became visible to the naked eye, and remained detectable for months before fading from view. Contemporary reports describe observers noting a new star that disrupted the familiar constellations. In many ways, Nova Cygni mirrors what V Sagittae will do. A faint or unseen star erupts into brilliance, dominates the night sky, and holds attention for an extended period. However, unlike V Sagittae, Nova Cygni's outburst was unexpected. Observers had no warning, no models predicting its appearance, and had to rely solely on chance to witness it. V Sagittae's predictability represents a profound departure from these historical novae. Another instructive comparison is Eta Carinae, the massive, unstable star in the southern sky that underwent its famous Great Eruption in the 19th century. Eta Carinae brightened dramatically, becoming one of the brightest stars in the night sky for several years before fading again. During this period, observers could see it even in twilight, a testament to its enormous energy output. Eta Carinae's eruption was fueled by processes very different from those in V Sagittae. It is a massive, luminous blue variable star, not a white dwarf accreting material from a companion. Nonetheless, the dramatic increase in brightness and its sustained visibility provide a useful analogy. Both events illustrate that stars can evolve in ways that produce sudden, almost miraculous visibility to observers on Earth. For Eta Carinae, the eruption occurred unpredictably. For V Sagittae, the event is forecast decades in advance, demonstrating our growing mastery of stellar astrophysics. Even more recent novae, such as Nova Persei 1901, further illuminate the contrast. Nova Persei was discovered by observers who noticed a previously invisible star suddenly shining brightly, peaking at magnitude 0.2, making it temporarily the brightest star in Perseus. Astronomers later studied its fading, tracking the expansion of ejected material and the spectral signatures of hydrogen, helium, and heavier elements. While V Sagittae shares a similar mechanism, accretion-driven nuclear burning on a white dwarf, the predicted magnitude is far more extreme, possibly reaching levels brighter than Venus and approaching the luminosity of the full moon. In addition, Nova Persei's discovery was serendipitous, whereas V Sagittae's eruption is deliberately anticipated, allowing the global scientific community to prepare in advance for the event. The historical record also emphasizes the rarity of witnessing such phenomena. While novae occur frequently across the Milky Way, most are faint, distant, or obscured by interstellar dust, making them invisible to casual observers. Only a small fraction reach brightness levels that make them easily visible without instruments. V Sagittae stands out precisely because it combines proximity, energy, and timing to produce an event that is both brilliant and accessible. It will not merely be a faint point on a photographic plate, it will dominate the sky in the way only a handful of historical events, Nova Cygni, Eta Carinae, and Nova Persei, have. Interestingly, Historical novae also provide insights into the potential evolution of V Sagittae's light curve. Many past novae exhibit an initial sharp rise in brightness, followed by fluctuations and a gradual decline over weeks or months. Some, like Nova Cygni 1670, showed multiple peaks in brightness, likely caused by interactions between ejected material and surrounding gas or residual accretion. V Sagittae may follow a comparable pattern, although the extreme mass transfer and the white dwarf's unique properties suggest that its initial peak could be far brighter and more sustained than most novae recorded in human history. This highlights how historical precedents offer both a guide and a contrast, showing what might be expected while underscoring the singularity of V Sagittae's event. From a human perspective, these historical comparisons deepen our sense of wonder. Observers in the 17th, 19th, and early 20th centuries were struck by novae they could not explain, events that seemed almost miraculous. Today, we understand the physics behind such eruptions, the accretion disks, the mass transfer, the nuclear ignition, but the emotional impact is no less profound. V Sagittae will allow modern humanity to connect with the same sense of awe experienced by past generations, while adding the extraordinary satisfaction of knowing the event in advance, having anticipated it through careful observation and modeling. In a way, V Sagittae represents both continuity and innovation. It is a natural successor to historical novae and stellar eruptions, following the same cosmic rules that govern all stars, yet it is unprecedented in the certainty with which we can predict it. Unlike Nova Cygni or Eta Carinii, which caught humanity by surprise, or Nova Persei, which required chance discovery, V Sagittae offers a pre-planned cosmic event, a convergence of astrophysics, observation, and human attention. Its magnitude, duration, and visibility set it apart, creating an extraordinary bridge between historical stellar phenomena and the future of observational astronomy. What makes V Sagittae truly extraordinary is its predictability. Across the history of astronomy, novae and other stellar explosions have usually caught observers completely by surprise. Humanity has witnessed them only after the event has begun, often as sudden flashes in the night sky, leaving astronomers scrambling to record, analyze, and explain phenomena they had not anticipated. For most of recorded history, a nova was a rare, serendipitous occurrence, a cosmic lottery in which observers might or might not be alive, looking up, or lucky enough to notice the star's transformation. V Sagittae breaks this pattern entirely. Astronomers today are not waiting passively for V Sagittae to erupt, they know when and where to look. This certainty is a result of decades of meticulous observation, combined with sophisticated modeling of binary star dynamics. V Sagittae's characteristics, the mass ratio of the two stars, the tightness of their orbit, the rate of mass transfer, and the properties of the white dwarf, have been carefully quantified. Using this data, astrophysicists can project the system's evolution forward in time. They can calculate when the donor star will be sufficiently stripped of mass, when the white dwarf will accumulate enough fuel, and when the runaway nuclear reactions will ignite. In other words, the star is not just a distant point of light, it is a cosmic clock whose final, brilliant minutes we can anticipate with astonishing precision. This level of predictability is unprecedented for an event of such magnitude. Most novae are discovered only after they have already flared, and in many cases, the precise mechanism or timeline of the eruption remains uncertain. In contrast, V Sagittae is effectively a pre-programmed supernova precursor, a system that has entered a runaway phase, with calculations pointing clearly toward a dramatic climax within the century. Astronomers are confident enough to give not only a year, 2083, but even to outline the likely progression of brightness over subsequent weeks and months. This foresight transforms V Sagittae from a mysterious, fleeting nova into a scheduled cosmic event, a celestial phenomenon that humanity can prepare to observe, study, and document in real time. Several factors contribute to this unique predictability. First, V Sagittae's binary nature is unusually well characterized. The orbital period, the masses of the stars, and the dynamics of the accretion disk are known with precision that is rarely possible for other nova candidates. Second, the runaway mass transfer is accelerating at a measurable rate. Decades of photometric and spectroscopic data reveal subtle increases in brightness and variations in spectral lines that reflect the growing instability of the system. By combining historical observations with models of stellar evolution, astrophysicists can extrapolate the timing of the final outburst with remarkable confidence. Third, The white dwarf's composition and size provide additional constraints. Since the amount of accumulated fuel required for runaway nuclear ignition can be estimated, the final eruption's magnitude and duration become predictable, not speculative. This combination of factors makes V Sagittae a once-in-a-lifetime event in more ways than one. It is not only spectacular because of its luminosity or proximity, it is remarkable because humans have the rare privilege of anticipating it. Whereas previous novae, Nova Cygni, Nova Persei, and Eta Carinae's eruption, occurred unpredictably, V Sagittae is a system whose drama is known in advance. Generations of scientists and stargazers can watch, measure, and document every phase of the eruption from its first flickers through its peak brilliance and gradual decline. This foresight allows for a level of preparation, observation, and analysis that no historical nova could have afforded. Predicting V Sagittae also represents a triumph of modern astrophysics. It demonstrates our ability to understand complex, interacting stellar systems not just qualitatively but quantitatively. We can model gravitational interactions, accretion dynamics, and nuclear reactions with sufficient accuracy to forecast an event decades before it occurs. In essence, we are witnessing a convergence of human intellect and cosmic processes, where careful observation and mathematical modeling allow us to anticipate a spectacle that would have been inconceivable to astronomers even a century ago. Beyond the scientific achievement, this predictability has profound cultural and psychological implications. Humanity will experience a stellar explosion not as a fleeting surprise but as a foreseen, shared event, allowing communities around the world to prepare, document, and collectively marvel at the unfolding drama. Children, students, educators, amateur astronomers, and professional scientists alike will all know in advance that a star is about to dominate the night sky, creating a rare global alignment of awareness, anticipation, and wonder. V Sagittae's uniqueness is thus multi-layered. It is extreme in brightness, unprecedented in naked-eye visibility, rare in proximity within our galaxy, prolonged in duration, and unparalleled in predictability. Together, these factors ensure that it will be remembered not only as one of the most spectacular astronomical events in human history but also as a landmark moment in our understanding of the universe. A star that allowed humans to see, decades ahead of time, exactly what was coming, and then witness it in all its glory. The year 2083 has emerged as the most likely timeframe for V Sagittae's climactic outburst not through guesswork or intuition, but through decades of careful observation, rigorous modeling, and an in-depth understanding of binary star physics. Predicting the precise timing of a stellar eruption is no small feat. Stars evolve over millions or billions of years, and most novae and supernovae appear without warning. Yet V Sagittae presents an unusual combination of circumstances that allow astronomers to calculate its impending eruption with a remarkable degree of precision, narrowing the event to within a few decades, a veritable instant in cosmic time. The foundation of this prediction lies in the rate of mass transfer between the donor star and the white dwarf. Observations over the past century, combined with modern photometric and spectroscopic data, have revealed that the donor star is losing mass at an accelerating rate. The star is distorted, swollen, and overfilled relative to its Roche lobe, meaning that each orbit contributes more material to the white dwarf than the last. By measuring the current luminosity, flickering behavior, and spectral features of V Sagittae, astronomers can estimate how much mass has already been transferred, how much remains, and the rate at which the process is accelerating. This provides a timeline for when the donor star will reach the critical mass threshold at which the white dwarf will ignite in a runaway nuclear explosion. Additionally, the orbital period of the system offers another key piece of the puzzle. V Sagittae is a close binary, with the two stars orbiting one another at incredible speed. Each orbit brings fresh material into the white dwarf's gravitational grasp. By monitoring variations in brightness that correspond to these orbital movements, astronomers can calculate exactly how rapidly material is being siphoned off. These data, when combined with models of stellar evolution, allow scientists to extrapolate forward, predicting not just if the eruption will occur, but when the system will reach the tipping point. The properties of the white dwarf itself also play a critical role in determining the timing. Astronomers know the white dwarf's mass, size, and density. They understand how much material it can accumulate before the pressure and temperature at the base of the accreted layer become sufficient to trigger runaway nuclear fusion. By estimating the remaining mass that must be transferred from the donor, and knowing the current transfer rate, they can project a window of time for the eruption. The combination of these measurements, donor mass, white dwarf capacity, and mass transfer rate, forms the backbone of the 2083 prediction. Advanced computer models have further refined this estimate. Astrophysicists simulate the complex dynamics of the binary system, accounting for the changing mass ratio, the evolving shape of the donor star, the structure and density of the accretion disk, and the feedback effects of the runaway process. These simulations allow scientists to observe virtual versions of V Sagittae evolving over decades and centuries, noting when conditions reach the point of instability that will lead to the outburst. The models consistently converge on a peak period around 2083, giving researchers confidence that this date is a credible estimate. Another factor in the calculation is historical data on similar systems. While V Sagittae is unique in its specific configuration, astrophysicists have observed other cataclysmic variables and binary systems with mass ratios approaching instability. By comparing the evolutionary trajectories of these analogues, scientists can cross-check their predictions and refine the expected timing. V Sagittae stands out because its combination of a massive donor star, a dense white dwarf, and extreme orbital proximity provides an unusually clean, measurable path toward a predictable eruption. Importantly, the few decades margin of error acknowledges the inherent uncertainties in stellar modeling. Although the observations and simulations are robust, stars are inherently chaotic systems, and minor variations in mass transfer rates or internal stellar physics can accelerate or delay the eruption. Scientists estimate that while 2083 is the most likely peak, the actual event could occur a few years earlier or later, or, in the extreme case, stretch toward the end of the 21st century. Still, the confidence interval is narrow enough to allow astronomers and enthusiasts to prepare in advance, a rare situation in the study of explosive stellar events. The calculation of the 2083 date is also a testament to the power of predictive astrophysics. Historically, stellar explosions were observed only after they occurred, leaving scientists to reconstruct the sequence of events retroactively. V Sagittae represents a reversal of that paradigm. Astronomers are observing the precursor phase, analyzing the mechanics, and using quantitative models to forecast the future. It is as if humanity has been granted a glimpse into the final act of a star's life before the curtains have even risen, a privilege almost unparalleled in the history of astronomy. In practical terms, the prediction allows decades of preparation. Observatories can schedule long-term campaigns to monitor subtle changes in the system leading up to the outburst. Space telescopes, ground-based observatories, and amateur astronomers alike will have the opportunity to capture the evolution of the system before it reaches its peak, providing a dataset unprecedented for a stellar explosion. By knowing the approximate date decades in advance, humanity can transform the eruption from a sudden surprise into a carefully documented, multi-generational event. The 2083 estimate also provides cultural and scientific context. Unlike historical novae or supernovae, whose appearance was sudden and unpredictable, V Sagittae allows the global population to anticipate a once-in-a-lifetime celestial event. People born today could grow up learning that in their lifetime, a star will blaze brighter than Venus, brighter than Sirius, and perhaps as bright as the full moon. The ability to assign a human-scale date to such an extraordinary event bridges the cosmic and the everyday, turning abstract astrophysics into a tangible, shared expectation. While the year 2083 stands as the central estimate for V Sagittae's dramatic outburst, scientists are careful to emphasize that this is not an exact expiration date stamped by the universe, but rather a best-fit prediction grounded in careful observation and modeling. Stars, particularly those in extreme binary systems like V Sagittae, are inherently dynamic and sometimes unpredictable. The processes driving the outburst, mass transfer, accretion, nuclear ignition, are governed by complex interactions that can vary over time, producing uncertainties that accumulate over decades. For this reason, astronomers assign a margin of error to the 2083 estimate, acknowledging that while the system is progressing toward eruption, it could ignite a little earlier, or a little later, anywhere within the span of the 21st century. This uncertainty arises from several factors. First, the rate of mass transfer from the donor star is accelerating, but the precise pace is difficult to model perfectly. Even small variations in stellar wind, surface convection, or magnetic activity can alter how rapidly material flows into the white dwarf's accretion disk. A slightly faster rate could precipitate the tipping point a few years or even a decade earlier than 2083, while a slightly slower rate could delay the outburst into the later decades of the century. The system's extreme closeness amplifies these effects. In a binary orbit measured in mere hours, small shifts in gravitational dynamics or stellar structure translate into significant differences in timing over the long term. Second, the white dwarf itself presents uncertainties. Its precise mass, internal composition, and thermal structure all influence how much accumulated material is required to trigger runaway nuclear fusion. Variations of just a fraction of a percent in these parameters can alter the timing of ignition. Furthermore, while we understand the basic physics of accretion and nuclear burning, the detailed microphysics, turbulence in the accretion disk, differential rotation, magnetic field interactions, introduces additional complexities that make absolute precision impossible. Third, the donor star is unstable and evolving. As it loses mass, it swells and distorts, which accelerates the transfer process, but the exact response of its envelope is sensitive to small fluctuations in internal pressure and temperature. In some models, the star could shed its outer layers faster than anticipated, pushing the system toward eruption slightly earlier than projected. In others, internal processes could temporarily slow the mass loss, giving the binary system a brief period of relative stability and delaying the outburst. These variations are subtle, but over decades they accumulate, creating a realistic window of uncertainty around the 2083 estimate. Finally, there is the challenge of long-term modeling itself. Astronomers rely on simulations to project decades of stellar evolution, incorporating everything from gravitational interactions to nuclear reaction rates. While modern computational methods are extraordinarily powerful, even minor approximations or unknown variables can shift predictions. In practice, this means that while 2083 represents the statistical best guess, a realistic margin of error extends perhaps a decade or more on either side. The eruption could plausibly occur anytime between roughly 2075 and 2095, giving humanity a window in which to witness the event rather than an exact calendar date. This margin of error does not diminish the excitement or significance of V Sagittae's predicted outburst. In fact, it enhances it in a unique way. The uncertainty adds a sense of suspense and anticipation. Generations of observers leading up to the event will be able to watch the system grow brighter, study subtle changes, and refine predictions as the explosion draws nearer. The years preceding the outburst will be a prolonged period of scientific observation, a countdown punctuated by increasing luminosity and growing signs of instability. Humanity will witness not only the peak moment of brilliance but also the system's approach, its tension building like a cosmic narrative unfolding across decades. Moreover, the margin of error highlights the dynamic and living nature of stars. Even in a system as well characterized as V Sagittae, slight variations can shift outcomes, reminding us that the universe is not fully deterministic from our perspective. The stars evolve according to physical laws, but small, interconnected processes, turbulent flows, magnetic fields, temperature gradients, can influence the timing of cataclysmic events. By accounting for a margin of error, scientists communicate both the confidence of their predictions and the humility inherent in studying phenomena on such grand scales. For the general public, understanding this uncertainty is crucial. It means that those alive today may witness the peak of V Sagittae's eruption if it occurs sooner, or they may only glimpse the initial brightening if the eruption is delayed. Yet regardless of the exact year, the event remains within the span of a human lifetime, a rare opportunity in cosmic terms. Unlike most supernovae or novae, which are unpredictable on short timescales, V Sagittae gives humanity a chance to prepare, observe, and study the explosion in unprecedented detail, even if the timing shifts slightly. Ultimately, the margin of error also reinforces the magnitude of the achievement in prediction. To forecast a star's explosion to within a few decades, based on the interplay of mass transfer, accretion, and nuclear ignition, is a triumph of modern astrophysics. It allows us to plan observations, coordinate global efforts, and educate the public, transforming what would otherwise be a chance astronomical curiosity into a scheduled cosmic event. The uncertainty adds drama, but it does not diminish the certainty that, sometime in the 21st century, V Sagittae will light up the night sky like no star ever has before. Despite the extraordinary power and brilliance of V Sagittae's predicted eruption, it is important to emphasize that this event poses no danger to life on Earth. While the term exploding star may sound ominous, the vast distances involved render any physical threat completely negligible. V Sagittae lies approximately 7,800 light-years away from our planet, deep within the Milky Way, in the small constellation of Sagitta. At this distance, even an eruption releasing energy equivalent to billions of suns will be reduced to a dazzling point of light rather than a destructive force. The outburst is entirely a visual and observational phenomenon for humanity, a spectacular light show, a cosmic fireworks display, rather than a hazard. To understand why it is safe, consider the types of radiation and energy that a stellar explosion emits. A white dwarf undergoing a nova-like eruption produces intense visible light, ultraviolet radiation, X-rays, and, in some cases, gamma rays. For objects within the immediate vicinity of the explosion, this can be catastrophic, stripping atmospheres or irradiating planets. However, at distances measured in thousands of light-years, these forms of energy are diluted over vast expanses of space. By the time the light reaches Earth, it has traveled across the galaxy and manifests primarily as an incredibly bright star in the night sky, intense enough to rival Venus or Sirius, perhaps even the full moon, but completely safe to observe. Even the strongest forms of stellar emissions, such as X-rays and gamma rays, are reduced to background levels by the intervening interstellar medium. Space itself acts as a natural filter, absorbing and scattering the most energetic radiation. Unlike a supernova occurring within a few dozen light-years, a scenario that could theoretically threaten life on Earth, V Sagittae is safely distant, and the energy it releases will be experienced solely as light visible from the surface. This makes the event perfectly safe for direct human observation, whether with the naked eye, binoculars, or telescopes. There is no need for protective equipment or concern about exposure. The visual spectacle alone will be extraordinary. As V Sagittae erupts, observers will see a previously faint star flare into prominence, bright enough to cast shadows at night. Its position in the constellation Sagitta will make it stand out dramatically against familiar stars. Over the following weeks or months, it will maintain its brightness, slowly fading while remaining visible across the globe. From the perspective of Earth, this will be a cosmic performance that rivals the most famous astronomical phenomena, but entirely benign in its physical effects. Moreover, the safety of this event allows scientists, educators, and the public to fully immerse themselves in observation without risk. Astronomers can deploy instruments to study the system across multiple wavelengths, capturing data on the accretion disk, the mass ejection, and the thermonuclear reactions occurring on the white dwarf surface. Amateur astronomers and casual stargazers can enjoy the show from their backyards, knowing that the event is both awe-inspiring and harmless. Unlike potentially dangerous cosmic events such as close supernovae or gamma-ray bursts, V Sagittae presents a rare opportunity to experience extreme astrophysics safely. This distinction between spectacle and danger also reinforces the wonder of the event. Humanity is being granted a window into a phenomenon that would normally be destructive or inaccessible, allowing us to witness the energy of billions of stars funneled into a single, beautiful burst of light. It is a reminder that the universe operates on scales far beyond human comprehension, yet occasionally allows us to observe its most dramatic processes without any personal risk. Historically, humans have often feared or misinterpreted bright transient events in the sky, seeing them as omens or threats. Nova sightings in centuries past, Nova Cygni 1670, Nova Persei 1901, and even the great eruption of Eta Carinii, sometimes caused anxiety simply because observers did not understand the nature of the events. Today, we know better. We can appreciate the beauty, the scale, and the physics of V Sagittae without fear. Its explosion is a celebration of cosmic dynamics, a reminder that the universe can be violent and energetic, yet entirely non-threatening at safe distances. In practical terms, Earthlings will experience this as a nighttime spectacle, a bright, luminous star dominating the night sky. Unlike phenomena such as meteor showers, which are brief and fleeting, V Sagittae will persist long enough to allow repeated observation, scientific documentation, and cultural reflection. Families, schools, observatories, and entire communities will be able to follow its evolution, enjoying the spectacle safely while learning about the underlying physics that drive such explosions. Ultimately, the safe yet spectacular nature of V Sagittae's eruption exemplifies a rare alignment of cosmic power and human perspective. It is a profound instance in which an extreme astrophysical process, capable of tremendous energy release on a stellar scale, becomes a benign visual wonder for humans across the globe. This reassurance transforms the event from a theoretical curiosity into an accessible, shared experience, one that will inspire awe, scientific inquiry, and global conversation for weeks and months as the star shines brighter than anything else in the night sky. Astronomers around the world are buzzing with anticipation at the prospect of V Sagittae's eruption. Unlike most stellar explosions, which are discovered only after the fact, this event is predicted decades in advance, allowing the scientific community to plan a comprehensive observational campaign that will be unprecedented in both scope and detail. For astrophysicists, V Sagittae represents a once-in-a-lifetime opportunity, a binary system transitioning from relative obscurity to a superluminous state under conditions that can be monitored in real time, from the buildup of mass transfer to the explosive peak and the gradual decline that follows. The excitement stems from both the scientific potential and the sheer visual impact. Observatories worldwide are already cataloging the system, monitoring subtle changes in brightness, spectral lines, and accretion disk dynamics. Instruments that detect electromagnetic radiation across the spectrum, from radio waves to X-rays, are being coordinated to provide a multi-wavelength view of the eruption. This is crucial because each part of the spectrum tells a different story. Radio waves reveal interactions of ejected material with surrounding space, infrared captures heat signatures, visible light shows the dazzling luminosity, and X-rays uncover the energetic processes at the surface of the white dwarf. By combining these data streams, scientists hope to construct a complete, three-dimensional picture of the event. Ground-based telescopes are preparing long-term observation programs. Some facilities will conduct continuous photometric monitoring, capturing changes in brightness hour by hour as the eruption begins and progresses. Others will focus on spectroscopy, dissecting the light into its component wavelengths to analyze the chemical composition, velocities, and temperatures of the expelled material. This will allow scientists to measure, in unprecedented detail, how the white dwarf burns through its accumulated hydrogen and helium, how the donor star reacts, and how the accretion disk evolves under the extreme conditions of a runaway explosion. Space-based telescopes are equally essential. Instruments like the Hubble Space Telescope, James Webb Space Telescope, and X-ray observatories such as Chandra can observe V Sagittae without interference from Earth's atmosphere, capturing high-resolution images and spectra across a broad range of wavelengths. These observations will be particularly valuable during the peak of the eruption when the system is at its brightest, providing data that ground-based telescopes may not be able to fully resolve due to atmospheric distortion or light scattering. Coordination between space and ground-based platforms will enable a continuous, high-fidelity record of the outburst, making it one of the most thoroughly documented stellar events in history. Astronomers are also preparing for the long-term follow-up. Unlike most novae, which fade quickly, V Sagittae is predicted to maintain extreme brightness for weeks, perhaps months. This extended visibility allows repeated observations at different stages of the eruption. Researchers will track the ejected material as it expands and cools, monitor variations in brightness caused by residual accretion, and examine interactions with the surrounding interstellar medium. The richness of the data will allow astrophysicists to test and refine models of binary evolution, accretion physics, and thermonuclear ignition on white dwarfs. The excitement is not confined to professionals. Amateur astronomers and citizen scientists are gearing up as well. Because V Sagittae will be visible to the naked eye worldwide, observers in cities, towns, and remote locations can participate in monitoring its evolution. Amateur astronomers equipped with telescopes, cameras, and spectrographs will contribute valuable data, creating a global network of observations that complements professional research. Schools and educational institutions can incorporate real-time monitoring into curricula, turning the event into a hands-on learning experience about the physics of stars, the dynamics of binary systems, and the scale of cosmic energy. In addition to observing the eruption itself, astronomers are also excited about studying the precursor behavior. Leading up to 2083, the mass transfer from the donor star is accelerating, creating subtle changes in the system's brightness and spectral features. Observing these precursors provides a rare opportunity to understand the final stages of binary instability in real time. Each incremental change, measured years or decades before the eruption, is a clue to the physics governing mass transfer, accretion disk dynamics, and the conditions that trigger a runaway thermonuclear event. This is something never before captured so comprehensively in human history. The community is also preparing for global coordination and public engagement. Astronomical societies, observatories, and science outreach organizations are planning campaigns to document the event, share data, and educate the public about what they are seeing. This is not merely a scientific exercise. It is a chance for humanity to collectively witness a cosmic event on a scale rarely experienced, turning V Sagittae into a shared moment of wonder and discovery. The combination of professional rigor and public engagement ensures that the eruption will be appreciated not only for its scientific significance but also for its ability to inspire curiosity and imagination. For astronomers, the anticipation is almost palpable. V Sagittae is a laboratory in the sky, offering insights into the physics of white dwarfs, binary evolution, accretion disks, and stellar explosions. It allows scientists to observe processes that normally unfold invisibly over millions of years, compressed into an observable period of weeks or months. The ability to track every stage, from mass transfer and disk formation to the explosive peak and gradual fading, is a dream scenario for astrophysicists, offering a level of detail and continuity never before possible. This excitement is compounded by the rarity of the opportunity. While novae occur frequently throughout the galaxy, the combination of proximity, brightness, predictability, and naked-eye visibility is unprecedented. Few, if any, other systems offer the chance to study such a dramatic event with foreknowledge, continuous observation, and global accessibility. In this sense, V Sagittae is not only a spectacular astronomical event but also a milestone in the history of observational astrophysics, a chance for humanity to witness, study, and understand a cosmic explosion in real time. Observing the eruption of V Sagittae promises to revolutionize our understanding of stellar evolution, particularly in the context of binary star systems, white dwarfs, and the physics of accretion-driven explosions. While astronomers have long studied these processes through theory, computer simulations, and indirect observations of other novae, V Sagittae provides a unique opportunity to see the entire sequence of a stellar catastrophe unfold in real time, from the final stages of mass transfer to the eruption and the subsequent cooling of ejected material. One of the most significant insights will come from studying the dynamics of mass transfer in extreme binaries. In V Sagittae, the donor star is being siphoned dry by the white dwarf at an accelerating pace. By monitoring how this material moves, accumulates, and forms an accretion disk, astronomers can test theoretical models of Roche-Lobe overflow and mass loss. These processes are central not only to nova formation but also to a range of stellar phenomena, including Type Ia supernovae, X-ray binaries, and even the formation of certain types of compact objects. Watching mass transfer escalate toward the tipping point allows scientists to validate or refine models that, until now, have largely relied on simulation or indirect observation. The eruption will also provide unprecedented insights into thermonuclear runaway reactions on white dwarfs. While the basic physics of hydrogen fusion under extreme pressure and temperature is well understood, real-world data from such events have historically been limited. By observing V Sagittae, astronomers will be able to track the ignition process across the white dwarf surface, study how the reaction propagates, and measure the resulting energy output. Spectroscopy will reveal which elements are produced and ejected during the explosion, shedding light on nucleosynthesis in compact stars. This knowledge can refine our understanding of how white dwarfs contribute to the chemical evolution of galaxies, distributing heavier elements into the interstellar medium over cosmic timescales. Another area of insight is the behavior of accretion disks under extreme stress. V Sagittae's disk is fed at an accelerating rate, creating turbulence, instabilities, and heating that drive observable flickering and emission features. By capturing the disk's behavior before, during, and after the eruption, astronomers can study angular momentum transfer, disk viscosity, magnetic field interactions, and the processes that trigger instability. These observations will have implications far beyond novae, informing our understanding of disks around young stars, neutron stars, black holes, and even protoplanetary systems. The eruption will also serve as a natural laboratory for studying binary star evolution and orbital dynamics. As the white dwarf consumes the donor star, the mass ratio of the system shifts dramatically, altering the orbit and the gravitational interactions between the two stars. Monitoring these changes in real time allows scientists to test models of orbital decay, tidal interactions, and stellar response to extreme mass loss. This is a rare opportunity to see how a close binary evolves on human observable timescales, rather than inferring behavior from distant systems or relying solely on simulations. Additionally, V Sagittae offers a chance to study the physics of stellar ejecta and shock interactions. As the white dwarf's eruption expels material at high velocity, it will interact with the residual gas in the system and the surrounding interstellar medium. Observing these interactions across multiple wavelengths, from optical to X-ray, will provide data on shock propagation, particle acceleration, and energy dissipation. This has implications not just for novae, but also for supernova remnants, planetary nebulae, and other astrophysical phenomena involving high-energy outflows. One of the most profound benefits of observing V Sagittae is the ability to connect the microphysics of stars with observable phenomena. The processes occurring on the surface of the white dwarf, nuclear burning, convective flows, magnetic interactions, will manifest as light variations, spectral lines, and changes in luminosity visible from Earth. By correlating theoretical predictions with these observable signatures, astronomers can validate models of stellar structure and behavior in unprecedented detail. This is a level of experimental astrophysics rarely available. Usually, stars evolve on timescales far longer than a human lifetime, leaving direct observation of dramatic change impossible. V Sagittae compresses centuries of evolutionary physics into months of observable behavior. Observing the system also provides insights into the late-stage evolution of intermediate-mass stars. The donor star in V Sagittae, once a relatively normal star, is being stripped of its outer layers. Monitoring how it reacts to this extreme mass loss, whether it puffs up, changes temperature, or exhibits variability, offers real-time data on stellar response to envelope depletion. These observations are crucial for understanding how stars end their lives, how white dwarfs gain mass, and under what circumstances such systems might eventually trigger Type Ia supernova, which are essential standard candles for measuring cosmic distances. Finally, V Sagittae has educational and public science benefits that complement its scientific value. By observing a major eruption in real time, students and amateur astronomers can learn firsthand about the physics of stars, the nature of binary systems, and the techniques used to study transient events. Every data point, photo, and spectrum captured worldwide will contribute not just to research but also to public understanding and appreciation of astronomy, creating a legacy of knowledge and engagement that spans generations. In essence, V Sagittae is a cosmic classroom, a laboratory, and a spectacle all in one. It allows humanity to witness processes normally hidden in the hearts of stars, to test and refine theoretical models, and to collect a trove of observational data unparalleled in human history. The eruption is not just a light show, it is an extraordinary opportunity to deepen our understanding of how stars live, interact, and die, illuminating the mechanics of the cosmos in a way that will shape astrophysics for decades to come. V Sagittae represents a truly once-in-a-lifetime event for humanity, not only because of its extreme luminosity and worldwide visibility, but also because of the extraordinary circumstances that allow us to predict its eruption decades in advance. In the vast timeline of the universe, where stars are born, live, and die over millions to billions of years, the probability that a human observer will witness a stellar explosion is vanishingly small. Most novae, supernovae, or other dramatic stellar phenomena occur at unpredictable times or at distances too great for the naked eye to detect. Yet here, in our own galaxy and within the span of a single human lifetime, a star will transform from a faint, invisible point into a radiant beacon in the night sky, a cosmic spectacle planned and anticipated by modern science. The rarity of such an event cannot be overstated. Consider the historical record. Most visible novae, like Nova Cygni in 1670 or Nova Persei in 1901, were discovered only after their brightness increased unexpectedly. Early observers had no warning, relying purely on chance to witness these phenomena. In contrast, V Sagittae's outburst is forecast, with scientists confident enough in their models to assign it a time frame within a few decades. This is unprecedented in the history of astronomy. Never before has humanity had the opportunity to watch a star build toward an eruption, to monitor the precursor activity, and then to observe the event's climax as it unfolds in real time. The ability to predict and prepare for a cosmic explosion of such magnitude is what makes V Sagittae a singular event in both human experience and scientific achievement. From a generational perspective, the timing is extraordinary. The eruption will occur during the 21st century, ensuring that people alive today, children, students, and working adults, may witness the phenomenon. Most astronomical events of comparable magnitude, such as supernovae in other galaxies, occur far too infrequently or too distantly to be directly experienced without specialized equipment. V Sagittae, however, will shine bright enough to be seen with the naked eye, creating a shared, global spectacle that stretches across continents. It is a convergence of opportunity, timing, and proximity that makes this eruption an event most humans will never have the chance to see again. The rarity is also underscored by the combination of features that V Sagittae exhibits. It is predictable, bright, visible worldwide, and prolonged in duration. Most novae are either brief or too faint, and even most nearby supernovae are unpredictable. Here, the system offers all these factors simultaneously. Observers will not only see a star reach incredible brightness but will have months to monitor and document its evolution, capturing every stage of the eruption in detail. Such a comprehensive viewing experience, occurring in a predictable window, is a phenomenon that human civilization is uniquely positioned to witness and record. For astronomers, the anticipation is more than professional excitement. It is a historic opportunity. To follow a star as it approaches its tipping point, to measure the acceleration of mass transfer, the growth of the accretion disk, and the subtle pre-eruption luminosity changes, is a privilege unlikely to recur in a single scientist's career. Observatories can design long-term studies, amateur astronomers can contribute systematically, and educators can create curricula that link real-time observation with astrophysical principles. The event will effectively compress centuries of stellar evolution into months of human observation, a rare alignment of cosmic processes and human attention. The uniqueness extends beyond science to the cultural and social experience. Imagine entire communities, schools, and families around the globe watching the same star gradually brighten over weeks or months, knowing that it is about to reach a pinnacle of luminosity unseen in generations. Unlike a solar eclipse or meteor shower, which recur periodically, the V Sagittae eruption is a one-off event in human observational history. People who witness it will carry that memory for the rest of their lives, and they will likely pass it down to future generations, creating a living narrative of cosmic wonder. Furthermore, the fact that this event can be shared globally in real time enhances its once-in-a-lifetime status. Technology will allow photographs, live feeds, and measurements from every continent to be combined into a collective record. Humanity will not experience this star in isolation. We will experience it as a species, united in observation, study, and appreciation. The eruption will become both a scientific milestone and a shared human memory, a rare intersection of cosmic scale and human perception. Finally, the event emphasizes how unusual it is to predict and witness such phenomena simultaneously. We are accustomed to studying stars after they have evolved or erupted, reconstructing history from light and spectra. V Sagittae allows us to observe the entire prelude and climax, from increasing accretion to the runaway nuclear ignition. Few, if any, other stellar events combine this predictive knowledge with actual observation. For most humans alive today, this may be the only opportunity in their lifetimes to witness a stellar explosion with such certainty, magnitude, and duration. In short, V Sagittae is a cosmic convergence of rarity, visibility, and predictability. It is not just a bright star in the sky. It is a once-in-human-lifetime phenomenon, a spectacle of physics, energy, and cosmic timing. Few events in history, or the foreseeable future, will allow humanity to both anticipate and fully observe the violent, beautiful climax of a star's life. The event will remain unmatched in the human experience of the cosmos, an extraordinary reminder of our ability to understand, anticipate, and witness the immense forces shaping the galaxy. V Sagittae's eruption is not just a scientific event. It is a story that will bridge generations, connecting those alive today with their children, grandchildren, and perhaps even great-grandchildren. The predicted peak in 2083 places the climax decades away from the present day, meaning that most of the current adult population will likely witness only the early signs of the star's transformation, its accelerating mass transfer, subtle increases in brightness, and the initial prelude to its eventual blaze. For many, the full spectacle of the eruption may occur when they are elderly or no longer able to observe directly, transforming V Sagittae into a tale that must be shared and passed down, much like the stories of past astronomical wonders such as Halley's Comet, Nova Persei, or the Great Eruption of Eta Carinii. This process of passing the story on has deep significance. It will become part of collective human memory, a narrative woven into family lore, educational systems, and cultural consciousness. Parents can point to the star in the sky and say, "This is the star that will shine brighter than Venus one day," inspiring curiosity and awe in children long before the eruption occurs. Astronomers and science communicators can use the decades leading up to 2083 to prepare educational programs, documentaries, interactive simulations, and citizen science projects that allow younger generations to engage directly with the unfolding science. By the time the eruption reaches its peak, children who have grown up with stories, images, and data about V Sagittae will witness the culmination of a narrative that began decades earlier, creating an intergenerational bond with the cosmos. The story of V Sagittae also offers a rare lesson in patience, observation, and scientific prediction. In a world accustomed to instant results and rapid technological change, the decades-long anticipation of a stellar eruption teaches humanity to think in cosmic timescales, to appreciate gradual processes, and to marvel at the slow build-up of forces that eventually manifest as spectacular phenomena. Parents, teachers, and mentors can use V Sagittae as a metaphor for careful preparation, cumulative effort, and long-term understanding, reinforcing values that extend beyond science into everyday life. Moreover, passing down the story is not merely about sharing facts, it is about sharing wonder. Imagine a child in 2080 hearing from a grandparent that a faint, barely visible star in Sagitta is about to become the brightest object in the night sky, capable of casting shadows and rivaling the full moon. The narrative transforms the cosmos into a living, evolving theater, where humans are not just observers but participants in a story that spans decades, bridging the present with the future. In this way, V Sagittae becomes part of human culture, a star that exists not only in the sky but also in the collective imagination. Scientific data will further enrich this transmission. Observations, images, and spectra collected in the years leading up to the eruption can be compiled into archives, shared digitally, and integrated into educational tools. Children learning about stars in 2083 will be able to study real-time data collected by scientists who witnessed the prelude and early build-up, providing a direct connection between theoretical physics and lived observation. This interweaving of personal experience, storytelling, and scientific record ensures that V Sagittae's eruption is both a cosmic event and a human narrative, one that is remembered, taught, and celebrated across generations. The anticipation also allows families and communities to plan for shared observation. Schools might organize nights to track the growing brightness, amateur astronomers can coordinate global monitoring campaigns, and families can take children outside to see the star slowly intensify over years. By the time the eruption reaches its peak, it will not just be a solitary observation. It will be a cultural milestone, a moment where stories, science, and human curiosity converge. Generations who pass these stories forward will embed the eruption into history and memory, much as past societies did with events like the comets of the 17th century or the supernova of 1054 that created the Crab Nebula. In this sense, V Sagittae becomes more than a stellar explosion. It becomes a temporal bridge, connecting the present with the future, the observer with the unobserved, and humans with the cosmos. The star's prelude is a teaching tool, its eruption a climax, and the stories pass down the threads that tie these events together. For most people alive today, the full spectacle may be slightly out of reach, but the knowledge, the excitement, and the cultural resonance will endure, creating a living legacy that children and grandchildren can inherit and experience. Ultimately, V Sagittae reminds us that the universe does not unfold on human timescales, but humans can still participate meaningfully in its stories. By preparing for and passing down the tale of this star, we ensure that the eruption is not merely a brief astronomical curiosity but a shared generational experience, an enduring connection between humanity and the cosmos, linking decades of anticipation with moments of awe and understanding. Events like the impending eruption of V Sagittae compel us to step back and reflect on the vastness and grandeur of the universe, and they remind us of just how small and fleeting human life is in comparison to the cosmic scales at play. In the night sky, a faint point of light, a star virtually invisible to the naked eye today, will, in a matter of decades, explode into brilliance so intense it can be seen from every corner of the Earth, rivaling Venus, Sirius, and perhaps even the full moon. The sheer magnitude of this transformation, the energy released, and the scale of the physical processes involved dwarf our daily concerns and human perspective, evoking a profound sense of awe, humility, and curiosity. When we contemplate that V Sagittae is located approximately 7,800 light-years away, we realize that the photons we will see in 2083 will have traveled across nearly 8 millennia of interstellar space. Every glimmer carries a story of gravitational forces, nuclear reactions, and complex binary interactions unfolding long before humans even existed. In that sense, the eruption is not only a spectacular visual display, it is a temporal bridge, connecting us to events that occurred far beyond the scope of human history and reminding us that the cosmos operates on scales of space and time that are almost incomprehensible. Observing such a cataclysm forces us to confront the reality that our existence is infinitesimal on the cosmic scale. Planets, stars, and galaxies operate according to fundamental physical laws that dwarf human lifespans and human history. The eruption of V Sagittae is just one of countless stellar events happening in the Milky Way and beyond, yet it will dominate our night sky, a reminder that the universe is constantly in motion, creating, destroying, and transforming matter across unimaginable distances. The universe is not static, it is dynamic, energetic, and full of processes that continue irrespective of human presence. This perspective can be both humbling and inspiring, emphasizing that while we are small, we are capable of understanding, predicting, and appreciating the mechanics of these cosmic phenomena. The wonder is heightened by the scale of energy involved in V Sagittae's eruption. As the white dwarf consumes its companion star and triggers a thermonuclear runaway, it will release energy equivalent to billions of times that emitted by the Sun every second. Yet, at a distance of thousands of light-years, this colossal energy manifests to us merely as a bright point in the night sky, a stark illustration of both the power of the cosmos and our relative vulnerability. It is a vivid lesson in scale. Enormous processes can occur silently across the galaxy, largely imperceptible until they interact with our senses. This duality, immense power rendered accessible yet safe, underscores the paradoxical beauty of the universe, overwhelming and majestic, yet approachable through observation and science. V Sagittae also exemplifies the interconnectedness of cosmic phenomena. The eruption we will witness is not a spontaneous event. It is the culmination of billions of years of stellar evolution, nuclear fusion, and orbital dynamics. The fate of the donor star and the white dwarf is determined by fundamental forces, gravity, thermonuclear energy, and angular momentum. The bright display in 2083 is the visible result of countless microscopic processes and interactions that have been unfolding long before humanity's existence. This connection between the immense and the minute, between the vast scales of time and space and the precise physics governing stars, evokes a sense of wonder at the elegant complexity of the cosmos. There is also an existential aspect to the reflection inspired by V Sagittae. Observing this event, even from a safe distance, invites us to contemplate our temporal insignificance and the fleeting nature of human life. The universe operates on timescales far longer than human history, and stars like V Sagittae evolve over millions or billions of years. Yet, within that vast timeline, humans have developed the ability to predict, anticipate, and study these events in detail. This duality, our smallness juxtaposed with our capacity for understanding, creates a profound sense of intellectual wonder. We are participants in a universe whose scales and energies far exceed our daily comprehension, yet we can, through observation and analysis, perceive and anticipate its processes. The eruption also highlights the beauty and unpredictability of the cosmos. While V Sagittae has been predicted, countless other stellar phenomena occur beyond our knowledge or reach. The fact that we can foresee one star's explosive outburst reminds us that the universe is a treasure trove of mysteries, some observable, some hidden, and that our pursuit of understanding is an ongoing adventure. Every new observation, every new prediction, deepens our appreciation of the universe's complexity and reminds us that our capacity to learn is both finite and extraordinary. Finally, the event emphasizes a shared human connection to the cosmos. V Sagittae's brilliance will be visible to people across the globe, uniting observers of different cultures, ages, and backgrounds in a common experience. In that moment, the star becomes more than a physical phenomenon. It becomes a symbol of collective human curiosity and the universal drive to explore and understand. We are reminded that while our lives are fleeting, our observations, knowledge, and stories about the universe endure, connecting us across generations and continents, and linking our small existence to the grand narrative of the cosmos. In essence, the eruption of V Sagittae will not merely be a spectacular light show. It will be a cosmic mirror, reflecting both the grandeur of the universe and the smallness of humanity. It will challenge us to contemplate our place in the vast tapestry of space and time, to marvel at the forces shaping stars and galaxies, and to embrace the humility and wonder that come from witnessing a universe that is infinitely larger, older, and more powerful than ourselves. In that reflection, we find both perspective and inspiration, a reminder that, while small, we are capable of perceiving, predicting, and appreciating the extraordinary drama of the cosmos. By 2083, the night sky will be transformed in a way that humanity has never witnessed. In the small, modest constellation of Sagitta, where once a faint, almost imperceptible star hovered unnoticed, V Sagittae will blaze with a brilliance that commands attention from every corner of the Earth. The star will no longer be a subtle point of light requiring telescopes or careful observation. It will dominate the heavens, shining brighter than Sirius, outshining Venus, and rivaling the luminosity of the full moon. Its light will pierce the darkness of night, casting a gentle glow over landscapes, illuminating rooftops, fields, and forests in a soft, silvery brilliance, a celestial presence that seems almost tangible. Amateurs and professional astronomers alike will gather their instruments, but even those standing beneath the sky with unaided eyes will feel the awe-inspiring magnitude of the event. The star will twinkle with a steady yet radiant intensity, a result of the energy released by the white dwarf as it consumed its companion in a cataclysmic finale. Those who witness it will see not just a star, but the story of millions of years of stellar evolution unfolding in real time. A narrative of gravity, nuclear fusion, and orbital dance made manifest in light visible across the globe. The entire night sky will seem subtly different because of V Sagittae's presence. Neighboring stars in Sagitta, once the primary markers of the constellation, will appear diminished in comparison. The Milky Way itself will seem to stretch and shimmer around this new point of intensity, highlighting the contrast between the serene backdrop of the galaxy and the violent drama of a binary system reaching its climax. Every glimmer, every faint star, will serve as a reminder of the delicate balance and the extraordinary rarity that allowed V Sagittae to reach such prominence. As weeks pass, the eruption will maintain its incredible brightness, gradually fading yet remaining conspicuous for months. Observers will witness subtle changes in hue and intensity as the ejected material expands and cools, offering both a spectacle and a lesson in astrophysics. The glow will paint the night sky with a kind of living artwork, constantly shifting yet maintaining a majestic dominance. For anyone watching, it will be a moment of cosmic communion, where humanity collectively experiences the grandeur and unpredictability of the universe firsthand. The visual will not merely be a static brilliance. Through telescopes and sensitive cameras, the accretion remnants and surrounding material may reveal intricate patterns, hints of swirling disks, and jets of expelled matter stretching outward, tiny echoes of the violent processes that created this luminous marvel. Scientists will be able to observe these fine details while everyday observers enjoy the simple, profound joy of seeing a new, extraordinary star in the sky. In living rooms, backyards, and mountaintops worldwide, people will share stories, photographs, and experiences, creating a global narrative that mirrors the cosmic drama above. From a philosophical perspective, the glowing V Sagittae will serve as a beacon of perspective. Children will look up and learn about stellar evolution, adults will be reminded of humanity's smallness in the cosmos, and everyone will be encouraged to reflect on the universe's vast timescales, its power, and the delicate balance that allows life to exist on a small blue planet orbiting an ordinary star. The eruption transforms the night sky into a visual metaphor for knowledge, curiosity, and anticipation, reminding all observers that while the universe is immense and indifferent, humans possess the unique ability to predict, witness, and learn from its wonders. As the months unfold, the star's brilliance will fade gradually, leaving behind subtle traces, remnants of ejected gas, faint radiation, and a transformed binary system now permanently altered by its cataclysmic past. Yet the memory of its brilliance will endure in human consciousness, in scientific records, and in the stories passed down from parents to children. V Sagittae will become a defining event of the early 21st century, a celestial landmark linking human curiosity with the eternal dance of the cosmos. Ultimately, the night sky of 2083 will not be merely a backdrop. It will be an active participant in human experience, glowing with the story of a star that, against the odds, revealed its destiny to us in advance. Observers worldwide will look up in awe, knowing that they are witnessing the culmination of a carefully predicted, unprecedented stellar event. A brilliant climax that will be remembered for generations, a radiant symbol of the wonders that await those who dare to watch the universe unfold. V Sagittae, once faint and obscure, will have become the crown jewel of the night sky, a living testament to the interplay of gravity, nuclear physics, time, and human curiosity, illuminating both the cosmos and our capacity for understanding. In 2083, the heavens themselves will narrate a story that spans eons, connecting humanity to the stars in a way that is both breathtaking and profoundly humbling. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.